documentary for sleep, hello there, and welcome. Tonight I want to take you somewhere special, somewhere far beyond the familiar glow of city lights and the comforting presence of our moon. I want to take you into the vast spaces between the stars, where darkness isn't empty but filled with possibilities we're only beginning to imagine. Perhaps you're settling in for the night, finding that comfortable position where your body can finally release the tensions of the day, and as you do, I invite you to let your mind drift with me into one of the cosmos's most intriguing mysteries. It's a question that might seem impossible to answer, yet holds within it a gentle fascination that has captivated astronomers and dreamers alike. What if, in the immense darkness between stellar systems, there are travellers we've never seen, ancient wanderers that have been drifting through space for billions of years, carrying with them secrets from the birth of stars and perhaps even the seeds of life itself? Before we continue on this journey together, and while you're getting comfortable wherever you're listening from tonight, I'd love to know where in the world you're joining me from. Whether it's late evening where you are, or perhaps you're listening in the early morning hours when the world is still quiet, please feel free to share in the comments below what time it is in your corner of our beautiful planet. And if this exploration of cosmic mysteries helps you find that peaceful state of mind we all seek at the end of the day, perhaps you'd consider subscribing to join me on future journeys through the wonders of our universe. There's something deeply connecting about knowing that people all around Earth are contemplating these same vast mysteries, each from their own unique place under the stars. So please, like this video if it resonates with you, and let's create a community of gentle wonder together. Now, as we begin to contemplate these dark comets that might drift between the stars, let's first acknowledge what might seem like skepticism. After all, comets are supposed to be bright, aren't they? We've all seen those magnificent images of Halley's Comet or Hale-Bopp, with their glowing heads and spectacular tails streaming across the night sky like cosmic calligraphy. These are the comets we know, the ones that announce their presence with brilliant displays as they sweep close to our sun. But what if these visible comets are merely the ones that happen to pass through our neighbourhood, while countless others, perhaps millions or even billions more, drift silently through the darkness, never coming close enough to any star to light up, never revealing themselves to our telescopes, yet carrying within their frozen cores materials that could rewrite our understanding of how the cosmos shares its treasures across impossible distances? Consider this for a moment, and let the idea settle gently into your consciousness like a leaf falling onto still water. The universe is approximately 13.8 billion years old, a number so vast that our minds can barely grasp its meaning. If you compressed all of cosmic history into a single year, with the Big Bang occurring at midnight on January 1st, our entire solar system wouldn't form until early September, and all of human civilization would flash into existence in the final seconds before midnight on December 31st. In all that time, in all those billions of years before our sun ignited, before Earth cooled from molten rock to blue marble, before the first life emerged from primordial seas, objects have been moving through space, propelled by the violent births and deaths of stars, sent on journeys that would last longer than our planet has existed. These dark comets, if they exist, and there's growing evidence that they might, would be like cosmic time capsules, preserving within their frozen hearts the conditions of space as it was billions of years ago. Unlike the comets we see, which are relatively young and still retain their volatile ices that sublimate into glowing halos when warmed by starlight. These dark wanderers would have long ago lost their ability to shine. They would have become something else entirely, something more like cosmic seeds, drifting through the eternal night, patient and silent, carrying their cargo of ancient materials from star system to star system without any conscious purpose, yet perhaps serving a purpose so profound that we're only beginning to glimpse its implications. The idea isn't as far-fetched as it might initially seem. In recent years, we've discovered objects that challenge our neat categories of what belongs where in space. Take Oumuamua, that strange visitor that passed through our solar system in 2017, moving too fast to be captured by our sun's gravity, clearly coming from somewhere else, somewhere beyond. While Oumuamua wasn't technically a dark comet, its discovery opened our eyes to the reality that objects do indeed travel between star systems, and if one could make such a journey and happen to pass close enough for us to detect it, how many others might be out there, passing through the darkness just beyond our ability to see. The mathematics of probability suggests something beautiful and humbling. If even a small fraction of the comets formed in the early days of each star system are ejected into interstellar space, and there are hundreds of billions of stars in our galaxy alone, then the spaces between stars might be populated with trillions upon trillions of these dark wanderers. They would be like a vast, invisible river flowing through the galaxy, connecting every star system to every other in a web of material exchange that operates on timescales we can barely imagine. Some astronomers have calculated that our own solar system might be visited by several of these interstellar objects every year, most passing through, undetected ghosts in the cosmic night. What makes this possibility so wonderfully contemplative is not just the science, though the science itself is fascinating, but what it means for our understanding of our place in the universe. We tend to think of star systems as islands, separated by vast gulfs of empty space that nothing can cross. But what if that's not true? What if the space between stars is actually filled with travellers, with messengers, with carriers of information and materials that connect every part of the galaxy in a slow but continuous exchange? The darkness between stars might not be empty at all, but filled with a vast migration of objects, each carrying within it the story of its origin, the chemical signature of the star that gave it birth, perhaps even organic molecules that could seed life on distant worlds. As you lie there tonight, perhaps feeling your breathing slow and deepen as we explore these ideas together, imagine for a moment that right now, at this very instant, one of these dark comets might be passing through our solar system. It would be invisible to our telescopes, too dark to reflect sunlight, too cold to emit infrared radiation, moving silently through the void, perhaps just beyond Neptune's orbit. It might have been travelling for 1 billion years or more, having been ejected from its home system when that star was young and violent, sent on a journey that would outlast the star itself. That star might now be a white dwarf, slowly cooling in some distant part of the galaxy, while this comet, this messenger from that long ago time, continues its eternal voyage. The chemistry locked within such an object would be extraordinary. In the deep cold of interstellar space, where temperatures hover just a few degrees above absolute zero, chemical reactions essentially stop. Molecules that would quickly break down in the warmth of a star system can remain stable for billions of years, Complex organic molecules, the kinds that serve as the building blocks of life, could be preserved in these cosmic freezers, waiting. Waiting for what? Perhaps waiting for nothing, simply existing in their frozen state forever. Or perhaps waiting for that rare encounter with a young star system where they might be captured by gravity and eventually deliver their cargo to a planet where conditions are just right for those molecules to wake from their long sleep and begin the complex dance of chemistry that leads to biology. This brings us to one of the most profound implications of dark comets drifting between the stars. We know that life on Earth is built from elements that were forged in the hearts of dying stars. The carbon in our DNA, the iron in our blood, the calcium in our bones, all of these were created in stellar furnaces and distributed through space by supernovae. But how exactly did these elements travel from those dying stars to the cloud of gas and dust that would eventually become our solar system? The traditional view is as they were simply mixed into the interstellar medium, the thin gas that fills the space between stars. But what if dark comets played a role in this distribution? What if they served as vehicles, carrying not just elements, but complex molecules, perhaps even primitive organic chemistry, from one stellar generation to the next? The gentle possibility emerges that life might not arise independently on each suitable world, but might instead be connected across the galaxy through these invisible threads of material exchange. This doesn't diminish the wonder of life on Earth. If anything, it enhances it, suggesting that we might be part of something even larger and more interconnected than we imagined. The molecules that make up your body right now might have travelled through space not just as individual atoms dispersed in gas clouds, but as part of complex structures preserved in dark comets, passed from star system to star system like cosmic messages in bottles, until finally, after journeys lasting billions of years, they found their way to Earth and became part of the grand experiment of life. Think about the profound patience of such a process. These dark comets don't hurry. They can't hurry. They move at velocities that seem fast by human standards, perhaps tens of kilometers per second. But given the vast distances between stars, their journeys take millions or billions of years. They are the ultimate expression of cosmic patience, carrying their cargo through the eons without any awareness of their role, without any intention, yet perhaps serving as crucial links in the chain of cosmic evolution. They remind us that the universe operates on timescales that dwarf human experience, that processes fundamental to our existence might unfold over periods so vast that entire species, entire worlds, entire stellar systems rise and fall while a single dark comet makes its way from one star to another. In our modern world, where everything seems to move at an ever-accelerating pace, where we measure success in quarters and years, where patience is often seen as a luxury we can't afford, these dark comets offer a different perspective. They suggest that some of the most important processes in the universe happen slowly, invisibly, without fanfare or recognition. They remind us that not everything needs to shine to be significant, that not every journey needs to be observed to be meaningful, that sometimes the most profound connections are the ones we never see. As we continue to explore this possibility together, let's also consider what it means for the search for life beyond Earth. We've spent decades looking for signals from alien civilizations, listening to the cosmos for any sign of intelligent communication. We've sent probes to Mars and the moons of Jupiter and Saturn, searching for signs of microbial life. But what if life's signature isn't just to be found on planets and moons? What if it also travels between the stars in these dark comets, preserved in ice and rock, waiting for the right conditions to emerge once again? The discovery of even simple organic molecules in an interstellar comet would revolutionize our understanding of how life might spread through the galaxy. Recent observations have given us tantalizing hints that this might indeed be happening. When Comet 2I/Borisov, the second confirmed interstellar object to visit our solar system, passed by in 2019, astronomers detected water, carbon monoxide, and other molecules in its coma, the cloud of gas that surrounds a comet's nucleus when it approaches the Sun. This was remarkable because it showed that interstellar comets can indeed carry complex molecules between star systems, but 2I/Borisov was still active, still outgassing, still visible. How many more such objects might there be that have long since gone dark, that no longer produce visible comas, that drift through space as silent carriers of cosmic chemistry? The technology to detect these dark comets is improving rapidly. New telescopes with unprecedented sensitivity are coming online, capable of detecting fainter objects than ever before. Machine learning algorithms are being developed that can sift through vast amounts of astronomical data, looking for the subtle, gravitational influences that might reveal the presence of dark objects passing through our solar system. Radio telescopes are becoming sensitive enough to potentially detect the faint thermal emissions from objects that are cold but not quite at absolute zero. Each advancement brings us closer to being able to see what has always been invisible, to detecting the dark wanderers that might be passing by right now. But perhaps the most beautiful aspect of this mystery is that we don't need to solve it completely to appreciate its implications. The mere possibility that dark comets drift between the stars, that they might be carrying materials from one stellar system to another, that they might play a role in the spread of life through the galaxy, this possibility itself enriches our understanding of the cosmos. It suggests a universe that is more connected than we thought, more dynamic than we imagined, more filled with potential than we dared to hope. It transforms the dark spaces between stars from empty voids into highways of cosmic commerce, where materials essential to life might be travelling even now, on journeys that began before our sun was born and will continue long after it has faded to darkness. Consider what this means for the future of life in the universe. If dark comets do indeed carry organic molecules between star systems, then life might be far more common than we currently believe. Instead of each planet needing to independently develop the complex chemistry that leads to biology, planets might be regularly seeded with the building blocks of life, delivered by these cosmic wanderers. The galaxy might be not a collection of isolated experiments in biology, but a vast interconnected laboratory where genetic and chemical information is constantly being exchanged, where life in one system can influence the development of life in another, even across distances that seem impossibly vast. This doesn't mean that life is inevitable on every suitable planet, of course. The conditions still need to be right. The planet needs to be at the right distance from its star, with the right atmosphere, the right chemistry, the right stability. But if the basic ingredients are being delivered regularly by dark comets, then perhaps the emergence of life is less of a rare accident and more of a natural consequence of cosmic evolution. Perhaps life is not the exception, but the rule, not confined to rare oases, but spreading through the galaxy like seeds on the wind, carried by these dark messengers that we're only now beginning to suspect exist. As you continue to relax into this exploration, letting these ideas wash over you like gentle waves, consider how this changes our perspective on our own existence. If dark comets have been delivering materials between star systems for billions of years, then the atoms in your body might have travelled through not just one or two stellar systems, but many. You might be made of materials that have witnessed the birth and death of dozens of stars, that have been part of other worlds, perhaps even other forms of life before finding their way to Earth. You are not just star stuff, as Carl Sagan famously said, but perhaps interstellar stuff, cosmic stuff that has been on journeys we can barely imagine. This cosmic heritage connects us not just to our own star, our own solar system, but to the entire galaxy. We are part of a vast material exchange that has been going on since the first stars formed, a process that will continue long after our sun has exhausted its fuel and Earth has become uninhabitable. The dark comets, if they exist, are the carriers of this heritage, the vehicles through which the galaxy shares its resources, its chemistry, perhaps even its life. They are the ultimate recyclers, ensuring that nothing is wasted, that the products of stellar evolution are distributed throughout the galaxy, available to contribute to new worlds, new chemistry, new possibilities for life. The search for these dark comets is not just a scientific endeavour, but a philosophical one. It asks us to reconsider our assumptions about how the universe works, about how isolated or connected different parts of the cosmos might be. It challenges us to think on timescales that stretch our imagination to its limits, to consider processes that unfold over billions of years as if they were natural and normal, which of course, on cosmic scales, they are. It invites us to see the darkness between stars not as empty or frightening, but as filled with potential, with travellers, with stories that we're only beginning to learn how to read. As we prepare to move deeper into this exploration, to examine the evidence for dark comets and what they might mean for our understanding of the cosmos, take a moment to appreciate the profound shift in perspective that this possibility offers. We're not alone in the universe, not because there are other civilizations sending us radio signals, but because we are part of a vast network of material exchange that connects every star to every other star, every planet to every other planet, through these silent, patient, eternal wanderers. The dark comets, whether we ever directly observe them or not, remind us that the universe is more interconnected than we imagined, that isolation is an illusion, that we are all, always, part of something larger. The gentle truth that emerges from contemplating dark comets is that mystery itself has value. We don't need to have all the answers to appreciate the beauty of the questions. The possibility that trillions of dark objects might be drifting between the stars right now, each one a time capsule from another era, another place, perhaps another form of life. This possibility enriches our experience of being alive in this cosmos. It adds depth to the darkness, meaning to the vast spaces that separate us from other stars, connection where we once saw only isolation. Tonight, as you drift towards sleep, you might imagine yourself as a passenger on one of these dark comets, frozen in time, patient beyond human comprehension, carrying within you the seeds of future possibilities. Your journey might take 1 billion years, but time would mean nothing to you in your frozen state. You would simply exist, moving through the darkness, occasionally passing close enough to a star to feel its distant warmth but never staying, always continuing on your eternal voyage. What would you witness on such a journey? the birth of new stars from collapsing gas clouds, their brilliant blue light illuminating the darkness for a cosmic moment before you passed back into the void. The slow spiral of galaxies as they rotate like vast pinwheels, though even their rotation would seem frozen from your perspective, so slowly do they turn. The occasional flash of a supernova, briefly outshining entire galaxies before fading back to darkness. And perhaps, just perhaps, after millions or billions of years, you would find yourself captured by the gravity of a young star, pulled into a new solar system where planets are still forming, where the chemistry of life is just beginning to stir. Your long journey would end as you delivered your cargo of ancient molecules to a new world, contributing your small part to the grand story of cosmic evolution. The materials you carried, preserved perfectly through your long voyage, would become part of new chemistry, new geology, perhaps eventually new biology. The connection between your origin and your destination, separated by unimaginable distances and eons of time, would be complete. This is the beautiful possibility that dark comets represent. They are not just chunks of ice and rock drifting through space, but threads in the vast tapestry of cosmic connection. They remind us that the universe is patient, that important processes can unfold over timescales that dwarf human comprehension, that not everything needs to be visible to be significant. They invite us to expand our perspective, to think beyond the boundaries of our solar system, beyond the lifespan of our species, beyond the age of our Earth, to see ourselves as part of a story that has been unfolding for billions of years and will continue for billions more. As we move forward in our exploration, we'll delve deeper into the science behind these possibilities, examine the evidence that suggests dark comets might indeed be real, and consider what their existence would mean for our understanding of life's place in the universe. But for now, in this moment of quiet contemplation, let's simply appreciate the wonder of the possibility itself. Somewhere out there, perhaps passing through our solar system at this very moment, there might be travellers from other stars, dark and silent, patient and eternal, carrying secrets we've yet to discover, connections we've yet to understand, possibilities we've yet to imagine. Between the stars lies an ocean of darkness vaster than human comprehension can hold, a void so immense that light itself becomes a weary traveller, taking years, decades, even millennia to cross from one stellar shore to another. As we continue our gentle exploration of dark comets that might drift through these cosmic spaces, we need to first understand the true scale of the canvas upon which these mysterious objects would paint their journeys. The space between stars is not just empty distance, but a realm with its own characteristics, its own subtle influences, its own quiet stories that unfold over timescales, that transform our understanding of what it means for something to exist, to travel, to carry meaning across the cosmos. Imagine, if you will, standing on Earth and looking up at the night sky. The stars seem close together, especially in the dense band of the Milky Way that stretches across the heavens like a river of light. But this is an illusion created by the vast distances involved. If we could shrink our solar system down so that Earth's orbit around the Sun was only 1 meter across, a comfortable step for most of us, then on this scale, the nearest star, Proxima Centauri, would be over 270 kilometers away. That's like standing in London and trying to see a meter-wide circle in Paris. The space between stars is so vast that even at the speed of light, the fastest speed possible in our universe, It would take over 4 years to make that journey. Now expand your imagination further. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars, each separated from its neighbours by distances typically measured in light years. The galaxy itself is about 100,000 light years across, which means that light leaving one edge of our galaxy when modern humans first emerged from Africa is only now reaching the other edge. In all that space, in all those vast distances between stars, we used to think there was nothing but the occasional hydrogen atom, a near-perfect vacuum more empty than anything we can create in our best laboratories here on Earth. But we're learning that this isn't quite true. The interstellar medium, as astronomers call it, is more complex, more structured, and possibly more populated than we ever imagined. The density of matter in interstellar space is almost incomprehensibly low. In the air you're breathing right now, there are about 10 to the power of 19 molecules in every cubic centimetre. That's a 1 followed by 19 zeros. In interstellar space, there might be just one atom in the same volume. It's an emptiness so profound that if you were to take all the matter in a cube of interstellar space the size of Earth and compress it down to the density of water, you'd have a sphere only about 15 meters across. This is the vast emptiness through which our hypothetical dark comets would travel, a void so empty that they could journey for millions of years without encountering anything larger than a microscopic dust grain. Yet this emptiness is not uniform. The interstellar medium has structure, like weather patterns in an almost infinitely thin atmosphere. There are regions where the density is slightly higher, molecular clouds where new stars are born, and regions where it's even lower, bubbles blown in the interstellar medium by ancient supernovae. There are magnetic fields threading through this space, invisible rivers of force that can deflect charged particles and influence the paths of objects passing through. There are cosmic rays, high-energy particles screaming through the void at nearly the speed of light. And there's the gentle pressure of starlight itself, photons from billions of stars creating a faint but persistent force that acts on everything in the galaxy. Through this complex, nearly empty space, our dark comets would drift like seeds on an impossibly thin wind. Their journeys would be influenced by forces so subtle that we can barely measure them, yet over the vast timescales involved, these gentle influences would shape their paths in profound ways. The gravity of passing stars, even stars light years away, would gradually bend their trajectories. The cumulative pressure of starlight from the entire galaxy would slowly push them in one direction or another. The magnetic fields would interact with any charged particles on their surfaces, creating tiny forces that, over millions of years, could alter their courses by millions of kilometers. Consider what it means for an object to travel through such a space. On Earth, we're used to friction, to air resistance, to things gradually slowing down and stopping unless we keep pushing them. But in the near-perfect vacuum of interstellar space, there's essentially no friction. A dark comet ejected from its home star system would continue moving at essentially the same speed forever, or at least for timescales so vast that forever becomes a reasonable approximation. If such an object were moving at a typical ejection velocity of, say, 20 kilometers per second, it would maintain that speed for billions of years, crossing the galaxy multiple times before the subtle influences of gravity and other forces significantly changed its motion. The temperature in interstellar space hovers just a few degrees above absolute zero, about 2.7 Kelvin to be precise, maintained by the faint afterglow of the Big Bang that still fills the universe with microwave radiation. This is cold beyond anything we experience on Earth, cold enough that even helium would be solid if there were enough of it in one place to form a solid. In this profound cold, chemical reactions essentially stop. Molecules that would quickly break down at Earth temperatures can remain stable for billions of years. This is why dark comets, if they exist, would be such perfect preservers of ancient chemistry. They would be like cosmic time capsules, their materials locked in a deep freeze that maintains them in essentially the same state they were in when they were ejected from their home systems. But even in this cold, empty space, things do happen, just very, very slowly. Cosmic rays, those high-energy particles racing through space, occasionally strike our hypothetical dark comets. Each impact might knock a few atoms off the surface, or might create brief, localized heating that allows chemical reactions to occur for just an instant before the cold reasserts itself. Over millions of years, these impacts could gradually erode the surface of a dark comet, creating a layer of processed material, a rind that's different from the pristine interior. This process, called space weathering, would slowly transform the surface while leaving the deep interior unchanged, creating objects with complex histories written in their layers like geological strata. The vastness of interstellar space also means that encounters between objects are extraordinarily rare. If dark comets are indeed drifting between the stars, the chances of any two of them colliding are essentially zero. They could pass within a few astronomical units of each other, a distance that seems small by interstellar standards, but is still hundreds of millions of kilometers, and continue on their separate ways, unaware of each other's existence. This isolation means that each dark comet would be a separate experiment in cosmic preservation, each maintaining its unique cargo of materials from its origin system without contamination from other sources. Yet despite this isolation, or perhaps because of it, the space between stars might be more crowded than we think. Not crowded in any conventional sense, of course, but populated with a vast number of these dark wanderers, each on its own journey, each invisible to our current instruments. Some astronomers have calculated that if even a small percentage of the comets formed in each star system are ejected into interstellar space, there could be more interstellar comets in our galaxy than there are stars. Think about that for a moment. For every star you see in the night sky, there might be thousands, perhaps millions, of dark comets drifting through the void, invisible and undetected. The distribution of these objects wouldn't be uniform. They would be more common near the plane of the galaxy, where most stars are located and where most ejection events would occur. They might form streams or rivers of objects, all ejected from the same system at roughly the same time, travelling together through space like a vast invisible caravan. Over time, these streams would disperse, their members gradually drifting apart due to tiny differences in velocity and the subtle influences of gravity from passing stars. But for millions of years they might maintain some coherence, a ghostly procession of dark objects sharing a common origin and a common journey. The speeds at which these dark comets travel would vary enormously. Some, ejected gently from their home systems, might be moving at just a few kilometers per second relative to the average motion of stars in the galaxy. These slow movers would take millions of years to travel from one star to its nearest neighbor. Others, ejected more violently, perhaps by close encounters with giant planets or by the gravitational chaos of binary star systems, might be moving at hundreds of kilometers per second. These fast movers would cross the galaxy in just a few 100 million years, cosmic bullets shooting through the void. The paths these objects take would be complex, influenced by the gravitational field of the entire galaxy. Unlike the neat elliptical orbits that comets follow within our solar system, the paths of interstellar comets would be chaotic, unpredictable, shaped by the combined gravity of billions of stars. They might spiral slowly around the galactic center, their orbits gradually precessing like a spinning top, slowly changing its axis of rotation. They might be deflected by close encounters with massive stars or giant molecular clouds, sent off on entirely new trajectories. Some might even be ejected from the galaxy entirely, sent on even longer journeys through the truly empty space between galaxies. In this vast dark ocean between the stars, time takes on a different meaning. For us, limited to lifespans measured in decades, even a journey to the nearest star seems impossibly long, but for a dark comet, time is essentially meaningless. It has no metabolism to slow, no consciousness to experience the passage of eons. It simply exists, moving through space with infinite patience, carrying its cargo of ancient materials toward an unknown destination. A journey of 1,000,000 years is no different from a journey of 1,000,000,000 years. The comet doesn't age in any meaningful way. It simply accumulates the subtle effects of cosmic ray impacts and the even subtler influences of interstellar chemistry. This brings us to a profound realization about the nature of interstellar space itself. It's not just a void to be crossed, but a realm where different rules apply, where processes that would be impossibly slow on Earth unfold naturally, where connections between distant places and times can be maintained across scales that challenge our understanding. The dark comets, if they exist, are not fighting against this vastness, but working with it, using the very emptiness and cold of interstellar space to preserve their materials, to maintain their integrity across cosmic time. The interstellar medium also has a history, a story of its own that our dark comets would witness in their long journeys. Billions of years ago, when the galaxy was younger, the interstellar medium was different. It contained fewer heavy elements, the products of stellar nucleosynthesis that have been gradually enriching the galaxy over cosmic time. The first dark comets, ejected from the first generation of stars, would have carried different materials than those ejected more recently. They would be archaeological artifacts from different epochs of galactic evolution, each preserving a snapshot of the conditions when and where they formed. As our galaxy has evolved, spiral arms have swept through the disk, compression waves that trigger star formation and stir up the interstellar medium. Dark comets would have witnessed these passages, perhaps being deflected by the increased gravity of the arms, perhaps passing through regions of slightly higher density where the thin interstellar gas is compressed. They would have witnessed the birth and death of millions of stars, each adding its contribution to the interstellar medium, each potentially creating new dark comets to join the vast migration. The galaxy has also experienced more violent events, collisions with smaller galaxies, the kinds of mergers that have happened several times in the Milky Way's history would have sent gravitational ripples through the entire system. Dark comets present during these events would have had their orbits disrupted, some perhaps gaining enough energy to escape the galaxy entirely, others being sent plunging toward the galactic center. These events would have mixed populations of dark comets from different regions, creating a complex distribution that reflects the entire history of our galaxy. Even now, as you contemplate these ideas, the space between the stars is not static but dynamic, constantly evolving on timescales we can barely perceive. Stars are moving relative to each other, some approaching, some receding, constantly rearranging the gravitational landscape through which dark comets must navigate. The spiral arms are rotating, though so slowly that their motion is essentially frozen from a human perspective. New stars are being born, adding their gravity to the complex field that shapes the paths of interstellar objects. Old stars are dying, some gently fading away, others exploding as supernovae that send shockwaves through the interstellar medium. These shockwaves from supernovae deserve special consideration. When a massive star explodes, it sends a blast wave expanding outward at thousands of kilometers per second, sweeping up the thin interstellar gas and compressing it into a shell. Any dark comets caught in the path of such a blast wave would suddenly find themselves in a very different environment. The normally thin interstellar medium would be compressed to densities millions of times higher, though still far less dense than Earth's atmosphere. The temperature would spike from near absolute zero to thousands of degrees, though only for the brief moment it takes the shock to pass. The dark comet might lose some of its surface material, vaporized by the sudden heating, but its interior would remain frozen, protected by its own bulk. After the shock passes, the dark comet would continue on its way, perhaps with a slightly altered surface, perhaps on a slightly different trajectory due to the momentum imparted by the blast wave, but essentially unchanged. It would carry with it the memory of this encounter, written in the modified chemistry of its surface layers, a record that could potentially be read billions of years later if the comet eventually entered another star system where observers with sufficient technology could study it. The magnetic fields that thread through interstellar space add another layer of complexity to the journeys of dark comets. These fields are weak by Earth standards, but extend over such vast distances that their cumulative effect can be significant. Charged particles on the surface of a dark comet would interact with these fields, creating tiny electric currents that could, over millions of years, the comet's rotation or even its trajectory. The fields themselves are constantly changing, twisted and tangled by the motion of stars and gas clouds, creating a complex, time-varying environment through which our dark wanderers must navigate. There's also radiation to consider, not just the cosmic rays we've already discussed, but the accumulated light from all the stars in the galaxy. This starlight, faint as it is in interstellar space, carries momentum. When photons strike the surface of a dark comet and are absorbed or reflected, they impart a tiny push. This radiation pressure is incredibly weak, but over millions of years it can have measurable effects. Depending on the size, shape, and surface properties of a dark comet, radiation pressure might gradually alter its orbit, perhaps pushing it toward or away from the galactic center, perhaps changing its velocity by a few meters per second over the course of millions of years. The shape of interstellar space itself, the way it's curved, by the gravity of all the matter in the galaxy, creates preferred paths and forbidden zones for our dark comets. There are regions near the galactic center where the gravitational fields are so complex and intense that any object entering them would be quickly ejected or torn apart. There are quiet regions in the galactic halo where an object could orbit for billions of years without significant perturbation. There are resonances, places where the orbital period of a dark comet might match some multiple of the galaxy's rotation period, creating stable or unstable configurations that could persist for eons or suddenly break apart, sending the comet on an entirely new path. Understanding this vast canvas helps us appreciate what a remarkable thing it would be for a dark comet to complete a journey from one star system to another. It's not just the distance that makes such journeys remarkable, but the navigation through this complex, ever-changing environment. The comet would need to maintain its integrity through millions of years of cosmic ray bombardment, survive any supernova shock waves it might encounter, navigate the complex gravitational fields of thousands of passing stars, and somehow arrive at another star system with its cargo of ancient materials intact. Yet the very vastness of space, the very factors that make such journeys seem impossible, also make them inevitable. Given enough objects and enough time, some will complete these journeys. It's a statistical certainty. If trillions of comets have been ejected from star systems over the history of our galaxy, then some of them, perhaps many of them, have successfully travelled from one system to another. They might be rare, these successful travellers, but in a galaxy with hundreds of billions of stars and billions of years of history, even rare events happen countless times. This is the profound beauty of the cosmic scale. Things that seem impossible from our limited perspective become not just possible, but inevitable when we expand our view to encompass the true scale of space and time. The dark comets, if they exist, are testament to this principle. Each one is an unlikely traveller, facing odds that seem insurmountable, yet collectively they might form a vast network of material exchange that has been operating since the galaxy was young. As we continue to contemplate these possibilities, we begin to see interstellar space not as a barrier, but as a medium through which slow but profound processes unfold. It's like an ocean where the currents are gravitational fields, where the islands are star systems, and where messages in bottles are dark comets drift slowly from shore to shore. Most never arrive anywhere, continuing their journeys forever through the void. But some, a precious few, wash up on distant shores, delivering their cargo of ancient materials to new worlds where they might contribute to new stories of cosmic evolution. The space between stars, vast and empty as it seems, is thus revealed to be full of potential, full of invisible travellers, full of connections we're only beginning to understand. It's a space where time is measured in millions of years, where distances are measured in light years, where processes unfold with a patience that transcends human comprehension. Yet it's also our space, the medium through which the materials that make up our world and ourselves have travelled, the canvas on which the story of cosmic evolution is written. What makes a comet dark is not absence but transformation through cosmic time, a gradual metamorphosis from brilliant messenger to shadow wanderer that speaks to the profound changes objects undergo during their eternal journeys through space. As we delve deeper into understanding these hypothetical dark comets, we need to explore what they might be made of, how they might have formed, and most importantly, how they could have transformed from the bright, active comets we know into the invisible travellers we're imagining. This transformation is not a death, but a different kind of existence, a state of being that might be far more common in our universe than the spectacular displays we occasionally witness when a bright comet graces our skies. To understand dark comets, we must first understand their bright cousins, those magnificent objects that have captured human imagination since the dawn of consciousness. A typical comet, the kind we can see and study, is often described as a dirty snowball, though this simple description hardly does justice to their complex nature. They are aggregations of ice, dust, and rocky material, held together by their own weak gravity and possibly by more complex forces we're still trying to understand. The ice isn't just water ice, but a complex mixture of frozen gases: carbon dioxide, carbon monoxide, methane, ammonia, and dozens of other compounds that would be gases at Earth temperatures but are solid in the deep cold of space. When one of these traditional comets approaches the Sun, something magical happens. The increasing solar radiation begins to heat the surface, causing the ices to sublimate, transforming directly from solid to gas without passing through a liquid phase. This creates the comet's coma, that glowing cloud that surrounds the nucleus, and the tail, that banner of gas and dust that can stretch for millions of kilometers. It's a spectacular process, but it's also a destructive one. Each pass near the Sun strips away some of the comet's material, gradually depleting its reservoir of volatile ices. After hundreds or thousands of passes, depending on how close the comet comes to the Sun and how much ice it originally contained, the comet might lose all its volatile materials, becoming what astronomers call an extinct comet. But what if a comet never gets the chance to make those repeated passes near a star? What if, instead of settling into a stable orbit within a star system, it's ejected into interstellar space, sent on a journey that will keep it far from any star's warming rays for billions of years? This is where our dark comets would be born, not in darkness but in exile, cast out from their home systems by gravitational interactions with planets or companion stars, beginning journeys that would transform them into something fundamentally different from their sun-grazing cousins. The process of ejection itself would be violent, but not necessarily destructive. Imagine a comet in the outer reaches of a young star system, perhaps in a region analogous to our Kuiper belt or Oort cloud. A close encounter with a giant planet, or perhaps the gravitational influence of a passing star, could accelerate the comet to escape velocity, sending it on a hyperbolic trajectory that would carry it out of the system entirely. The comet would experience intense tidal forces during the encounter, but if it survived intact, it would emerge into interstellar space with all its original material preserved, beginning its transformation into a dark comet. The first stage of this transformation would be thermal. As the comet moved away from its parent star, it would cool to the ambient temperature of interstellar space, those few degrees above absolute zero we discussed earlier. This cooling would be gradual at first, then increasingly rapid as the comet moved beyond the star's influence. Within perhaps a few thousand years, a cosmic eye blink, the entire comet would be in thermal equilibrium with interstellar space. At these temperatures, even the most volatile compounds would be frozen solid, locked in a crystalline matrix that could preserve them for billions of years. But the transformation wouldn't stop there. Over millions of years, cosmic rays would bombard the comet's surface, breaking molecular bonds and creating new compounds. This process, called radiolysis, would gradually create a crust of processed material on the comet's surface. This crust would be darker than the pristine ice beneath, as the broken and reformed molecules would absorb light rather than reflecting it. The comet would literally darken over time, becoming less and less reflective, less and less visible to any telescopes that might be searching for it. The interior of the dark comet, however, would remain largely pristine. Cosmic rays can only penetrate so far into solid material, perhaps a few meters at most. Below this processed crust, the original ices and dust would remain unchanged, a frozen record of conditions in the comet's original star system. This creates a fascinating dichotomy: a dark, processed exterior hiding a pristine interior, like a cosmic seed with a hard shell protecting the vital materials within. The composition of these dark comets would depend on where and when they formed. Comets that formed in the outer regions of star systems, where temperatures were always low, would be rich in volatile ices. Those that formed closer to their stars might have less ice, a more rocky material. Comets from very young star systems might be composed primarily of hydrogen and helium compounds, while those from older systems might be enriched with heavier elements produced by previous generations of stars. Each dark comet would thus be a unique sample of its place and time of origin, a frozen archive of cosmic history. One of the most intriguing aspects of dark comets is what might be preserved within their icy matrices. Laboratory experiments have shown that when simple molecules are exposed to radiation in conditions simulating space, they can form more complex organic compounds. Amino acids, the building blocks of proteins, have been created in such experiments. Nucleotide bases, the letters of the genetic alphabet, have also been synthesized. If these processes occur in the laboratory, they almost certainly occur in space as well, potentially within the ice of dark comets. This means that dark comets might not just be passive carriers of material, but active chemical laboratories, albeit ones that operate on geological timescales. The combination of cosmic ray radiation, the presence of simple organic molecules, and billions of years of time might lead to the formation of increasingly complex compounds. Not life, certainly, but perhaps some of the complex molecular machinery that life requires. When such a dark comet eventually enters another star system, it might deliver not just raw materials but prefabricated components that could jumpstart chemical evolution on a suitable planet. The physical structure of dark comets would also evolve over time. The constant bombardment of cosmic rays and micrometeorites would gradually erode the surface, but in the absence of gravity strong enough to pull the eroded material away, much of it would remain near the comet, perhaps forming a loose cloud of particles travelling along with the main body. This cloud would be invisible to our telescopes, but might play an important role in the comet's eventual fate. If the dark comet eventually entered another star system, this cloud of particles might be the first part to interact with the stellar wind, potentially creating a brief, faint signature that could alert observers to the comet's presence. The size distribution of dark comets would likely follow a power law, with many small objects and fewer large ones. The smallest dark comets might be just meters across, tiny chunks of ice and rock carrying only a few kilograms of material between the stars. The largest might be hundreds of kilometers across, massive enough that their own gravity would give them a roughly spherical shape. Most would probably fall somewhere in between, irregular chunks tens to hundreds of meters across, large enough to survive billions of years of erosion but small enough to be easily ejected from their home systems. The rotation of dark comets adds another layer of complexity to their nature. Most comets rotate, spinning slowly in space like cosmic tops. This rotation would continue in interstellar space, modified only by the tiny torques from symmetric outgassing during ejection or from impacts with cosmic dust. Over billions of years, this rotation might cause the comet to experience cycles of heating and cooling, as different faces are exposed to the cosmic microwave background radiation. These cycles would be incredibly subtle, temperature variations of perhaps a fraction of a degree, but over cosmic time, they might lead to interesting chemical and physical processes within the ice. Some dark comets might be binary or multiple systems, two or more chunks of ice and rock orbiting their common center of mass as they drift through space. These binary dark comets would be particularly interesting, as the gravitational interaction between the components might cause periodic stress and flexing, potentially creating cracks and fissures that could expose fresh material to space. The orbital evolution of such systems over billions of years would be complex, influenced by tidal forces, the Yarkovsky effect from asymmetric thermal radiation, and the gradual loss of angular momentum through gravitational wave radiation, though this last effect would be almost immeasurably small. The porosity of dark comets is another crucial aspect of their nature. Many comets appear to be quite porous, with densities suggesting they're more like loosely consolidated rubble piles than solid chunks of ice and rock. This porosity would affect how dark comets interact with their environment. Cosmic rays might penetrate deeper into a porous structure, processing material throughout the interior rather than just at the surface. Gas molecules from the interstellar medium might slowly diffuse into the pore spaces, becoming trapped and adding to the comet's inventory of materials. The porosity might also make dark comets more fragile, more likely to fragment if they encounter strong tidal forces when passing close to a star. The chemical evolution of dark comets over billions of years is a fascinating subject that we're only beginning to explore theoretically. In the deep cold of interstellar space, most chemical reactions would be impossibly slow, but some might still occur. Radioactive decay of unstable isotopes within the comet would provide a tiny but constant source of heat and ionizing radiation. This internal radiation might drive chemical reactions deep within the comet, creating pockets of complex chemistry isolated from the surface. Over billions of years, these pockets might develop into chemical environments unlike anything we've observed in our solar system. The surface chemistry of dark comets would be particularly exotic. The constant rain of cosmic rays would create a population of free radicals, molecules with unpaired electrons that are highly reactive. On Earth, free radicals quickly react with other molecules, but in the cold of interstellar space, they might remain stable for millions of years, building up to concentrations impossible to achieve in any terrestrial laboratory. If a dark comet with such a surface entered a star system and began to warm, these free radicals might suddenly become reactive, creating a burst of chemical activity that could synthesize complex molecules in ways we've never observed. The mineralogy of dark comets would also be unique. The dust grains embedded in the ice would have their own complex history, perhaps having been processed in the atmosphere of a dying star, shocked by a supernova, or altered by chemical reactions in the protoplanetary disk where the comet formed. These grains might include presolar grains, particles that predate our solar system and carry isotopic signatures of their stellar birthplaces. They might include calcium-aluminum-rich inclusions, the first solids to condense from the solar nebula. They might include organic globules, tiny spheres of complex carbon compounds that could serve as templates for further chemical evolution. The magnetic properties of dark comets could be surprisingly important. Some of the dust grains might be magnetic, containing iron or other ferromagnetic materials. Over billions of years in the weak magnetic fields of interstellar space, These grains might gradually align, creating a weak but measurable magnetic field for the comet as a whole. This field might interact with the interstellar magnetic field, creating tiny forces that could alter the comet's trajectory or rotation. It might also play a role in the comet's eventual interaction with another star system, as the magnetic field would interact with the stellar wind and potentially create observable phenomena. As we contemplate the nature of dark comets, we begin to see them not as dead, inert objects, but as complex evolving systems with their own subtle dynamics. They're archives of cosmic history, chemical laboratories operating on geological timescales, and potential seeds for future chemical and perhaps biological evolution. Each one would be unique, shaped by its origin, its journey, and the countless small influences it encountered along the way. Together, they would form a vast invisible population of objects connecting every part of the galaxy in a slow but continuous exchange of materials and information. The transformation from bright comet to dark comet is thus revealed to be not a degradation, but an evolution, not a death, but a metamorphosis into a different kind of existence. These dark wanderers would be the universe's way of preserving and transporting materials across otherwise impossible distances and times. They would be cosmic messengers, carrying information about distant stars and ancient times to futures and places their creators could never imagine. In their darkness, they would hold light from stars that died billions of years ago. In their frozen silence, they would carry the potential for future noise and activity when conditions are right. Scientists peer into darkness, finding hints of objects that shouldn't be there, gravitational whispers that suggest presences we cannot see, influences we cannot fully explain, and patterns in the data that speak of a hidden population of cosmic wanderers. As we explore the evidence for dark comets drifting between the stars, we enter the realm where observation meets theory, where careful measurements and statistical analyses reveal patterns that might indicate vast populations of invisible objects. This evidence doesn't come from direct observation, for by their very nature, dark comets would be nearly impossible to see, but rather from the subtle influences they would have on things we can observe, from the unexpected visitors that occasionally grace our solar system, and from our growing understanding of how planetary systems form and evolve. The story of evidence for dark comets begins, paradoxically, with objects we can see. In recent years, we've discovered two confirmed interstellar visitors to our solar system, Oumuamua in 2017 and Tui Borisov in 2019. These objects prove definitively that material does travel between star systems, that the barriers we once thought absolute are actually permeable. But for every interstellar object we detect, passing close enough to the Sun to be visible to our telescopes, statistics suggest there must be thousands, perhaps millions more passing through the outer solar system, too far away and too dark to see. These invisible passages leave no direct trace, but their cumulative effect might be detectable in other ways. Consider the mathematics of probability. If we've detected two interstellar objects in just a few years of looking with modern telescopes, and if our detection efficiency is as low as astronomers estimate, then the actual number of such objects passing through our solar system must be enormous. Some calculations suggest that at any given moment there might be thousands of interstellar objects within the orbit of Neptune, drifting silently through our cosmic neighbourhood. Most of these would be dark, having long ago lost any volatile ices that might make them visible. They would be the dark comets we're contemplating, invisible travelers from other stars passing through our solar system like ghosts. The orbital dynamics of long-period comets in our own solar system provide another line of evidence. These comets, which take thousands or millions of years to complete a single orbit, come from the Oort cloud, that vast spherical shell of icy bodies that surrounds our solar system at distances of up to a light year from the Sun. But when astronomers carefully analyze the orbits of these comets, they find subtle anomalies. Some comets seem to have orbits that are slightly more energetic than they should be, as if they've been given a small gravitational boost. Others have orbits that are oriented in unexpected directions, not aligned with the plane of the solar system as we might expect. These anomalies could be explained by the gravitational influence of passing stars, but the numbers don't quite add up. The known stellar encounters in our solar system's history can't account for all the orbital peculiarities we observe. This has led some astronomers to propose that invisible masses, perhaps dark comets from other star systems passing through the Oort cloud, might be responsible for some of these gravitational perturbations. Each individual encounter would be tiny, barely measurable, but over millions of years the cumulative effect of many such encounters could significantly alter the orbits of Oort cloud comets. The distribution of small bodies in our outer solar system also hints at invisible influences. The Kuiper belt, that region of icy bodies beyond Neptune, has a structure that's hard to explain with just the known planets. There are gaps where we'd expect to find objects, concentrations where theory suggests there should be fewer, and orbital alignments that seem too organized to be random. While much of this structure can be explained by Neptune's gravity and the early evolution of our solar system, some features remain mysterious. Could passing dark comets, invisible and undetected, have played a role in sculpting the outer solar system? Moving beyond our solar system, we find evidence in the observations of protoplanetary disks around young stars. These disks, where planets are currently forming, show structures that aren't easily explained by the gravity of forming planets alone. There are gaps and rings, spiral patterns and asymmetries, some of which might be caused by planets we can't yet detect, but others might be the result of interstellar objects passing through the disk. If dark comets are as common as some theories suggest, then every protoplanetary disk should experience multiple encounters with them during the millions of years it takes planets to form. These encounters could affect the distribution of material in the disk, potentially influencing where and how planets form. The chemical composition of meteorites provides another intriguing line of evidence. Some meteorites contain isotopic anomalies, ratios of different isotopes that don't match what we'd expect from material that formed in our solar system. While most of these anomalies can be explained by pre-solar grains, particles that formed around other stars and were incorporated into the solar nebula before our Sun formed, some remain puzzling. Could these anomalies be evidence of material delivered to our solar system by dark comets, either during its formation or more recently? The idea is speculative, but it's consistent with what we know about how isotopes are produced in different stellar environments. Observations of white dwarf stars have revealed something unexpected that might relate to dark comets. White dwarfs are the remnants of stars like our Sun, dense objects about the size of Earth but with masses comparable to the Sun. Their strong gravity should quickly pull any heavy elements in their atmospheres down into their interiors, leaving only hydrogen and helium visible. Yet many white dwarfs show evidence of heavier elements in their atmospheres, elements that must have been deposited recently. astronomically speaking. The leading explanation is that these white dwarfs are accreting material from asteroids or comets that have been perturbed into death spirals. But what perturbs these objects? In some cases, it might be dark comets from interstellar space, passing through the white dwarf's planetary system and gravitationally disturbing the orbits of local bodies. The study of stellar kinematics, the motions of stars through space, provides indirect evidence for a large population of dark objects in our galaxy. When astronomers measure the total mass of our galaxy based on the motions of stars, they find more mass than can be accounted for by visible stars, gas and dust. While most of this missing mass is thought to be dark matter, an exotic form of matter that doesn't interact with light, some small fraction might be ordinary matter in the form of dark comets and other invisible objects. The amount wouldn't be large, perhaps only 1% or 2% of the missing mass, but it would still represent trillions upon trillions of dark comets drifting through interstellar space. Gravitational microlensing surveys have occasionally detected events that might be caused by dark comets. When a massive object passes between us and a distant star, its gravity can focus the star's light, causing a temporary brightening. Most microlensing events are caused by stars or planets, but some show characteristics that are hard to explain. They're too brief to be caused by stars, but the implied masses are wrong for planets. Could some of these events be caused by dark comets passing close to our line of sight to distant stars? The statistics are still too poor to say definitively, but as microlensing surveys become more sensitive and cover more of the sky, we might be able to detect the gravitational signatures of dark comets directly. The phenomenon of interstellar dust provides another piece of the puzzle. We know that dust grains drift through interstellar space, and we can detect them when they enter our solar system. But the size distribution of this dust is puzzling. There seem to be fewer large grains than we'd expect if the dust were simply produced by collisions between asteroids or the stellar winds of dying stars. One possible explanation is that the large grains we're missing are actually small dark comets, objects just a bit too large to be called dust, but too small and dark to be detected by our current instruments. These microcomets might make up a significant fraction of the solid material drifting through interstellar space. Recent observations of the interstellar medium have revealed unexpected structures that might be related to dark comets. Radio telescopes have detected small, dense clumps of gas that shouldn't be stable according to our current understanding of interstellar physics. These clumps should disperse quickly, yet they seem to persist. One possibility is that they're held together by the gravity of invisible masses, perhaps collections of dark comets that happen to be travelling together. If true, this would suggest that dark comets aren't uniformly distributed through space but sometimes cluster together, perhaps because they were ejected from the same star system at roughly the same time. The search for extraterrestrial intelligence, SETI, has produced null results that might paradoxically support the existence of dark comets. One proposed solution to the Fermi paradox, the question of why we haven't detected signs of alien civilizations despite the vast number of potentially habitable planets, is that interstellar travel is more difficult than we think. But if dark comets are common, they would provide a natural means of transport between star systems, albeit a slow one. The fact that we haven't been visited by alien probes might suggest that dark comets, while common, don't provide an efficient means of directed interstellar travel, perhaps because their trajectories are essentially random and uncontrollable. Computer simulations of galaxy formation and evolution, increasingly include populations of dark comets to match observations. When astronomers simulate how galaxies form and evolve over billions of years, they need to include all significant sources of matter and gravity. Models that include reasonable populations of dark comets, based on what we know about how planetary systems eject small bodies, produce results that better match observations than models that don't include them. This isn't proof that dark comets exist, but it suggests that something like them is necessary to fully explain the structure and evolution of galaxies. The detection of complex organic molecules in interstellar space provides indirect support for dark comets as carriers of prebiotic chemistry. Radio telescopes have detected dozens of different organic molecules in interstellar clouds, including amino acids and other building blocks of life. While some of these molecules form in the gas phase, others might require solid surfaces to catalyze their formation. Dark comets, with their easy surfaces and long residence times in interstellar space, would provide ideal laboratories for the formation of complex organic molecules. The detection of these molecules in space suggests that the chemistry we imagine occurring on dark comets does indeed take place. Observations of cometary reservoirs in other star systems have revealed patterns that might indicate widespread ejection of comets into interstellar space. When astronomers observe the dust disks around other stars, they can estimate how many comets must be present to produce the observed amount of dust through collisions. In many cases, the number of comets seems to decrease over time faster than can be explained by collisions alone. This suggests that comets are being removed from these systems by some other process, with ejection into interstellar space being the most likely explanation. If this is happening around other stars, it strengthens the case that our galaxy is filled with dark comets, ejected from billions of planetary systems over cosmic time. The study of impact craters on airless bodies in our solar system provides another line of evidence. The Moon, Mercury, and the moons of the outer planets preserve records of impacts going back billions of years. When scientists analyze the size distribution and ages of these craters, they find evidence for changes in the impact rate over time. Some of these changes correspond to known events in our solar system's history, but others are harder to explain. Could some of the variation in impact rates be due to encounters with streams of dark comets from interstellar space? The evidence is circumstantial, but it's consistent with the idea that our solar system periodically passes through regions of higher dark comet density as it orbits the galaxy. These dark comets, if they exist, carry within them the memory of stellar births, their journeys spanning epochs that make human history seem like a single heartbeat in the vast rhythm of cosmic time. As we contemplate the temporal dimension of dark comet journeys, we enter a realm where our normal concepts of past, present, and future become fluid, where processes that would seem impossibly slow from our perspective unfold naturally, and where the distinction between journey and destination becomes meaningless. Time for these cosmic wanderers is not measured in the cycles of planets around stars, but in the slow rotation of galaxies, the gradual evolution of stellar populations, and the patient transformation of matter from one form to another across eons that dwarf any human experience of duration. To truly appreciate the journeys of dark comets through time, we must first adjust our temporal perspective, stretching our imagination to encompass scales that our evolution never prepared us to grasp. A human lifetime, roughly a century at most, is to a dark comet's journey what a single vibration of an atom is to our lifetime. If we could compress a billion-year journey of a dark comet into a single human lifetime, then each of our years would flash by in less than 3 milliseconds. Each day would last about 8 microseconds, and our entire recorded history would be over in about 15 seconds. From the perspective of a dark comet, human civilization doesn't even qualify as an event. It's more like a quantum fluctuation, a brief statistical anomaly in the otherwise smooth flow of cosmic time. Let's follow a hypothetical dark comet on its journey through time, beginning at its birth in a young star system perhaps 10 billion years ago. The universe was different then, younger and smaller, with fewer heavy elements and fewer generations of stars having lived and died. Our comet forms in the outer reaches of its stellar system, slowly accreting from the disk of gas and dust surrounding a young star. This process itself takes millions of years, as tiny grains stick together, forming larger and larger aggregates, until finally our comet reaches its final size, perhaps a few kilometers across, a mixture of ice and rock that reflects the composition of the nebula from which its star was born. For the first few million years of its existence, our comet orbits peacefully in the outer reaches of its star system. It witnesses the formation of planets closer to the star, watches as the protoplanetary disk dissipates, blown away by the young star's fierce stellar wind. It might have siblings, other comets formed at the same time, all following their slow orbits in the cold darkness far from their sun. This is a period of relative stability, but it cannot last. Young star systems are chaotic places, with planets migrating, orbital resonances developing and breaking, and gravitational perturbations accumulating over time. The event that sends our comet on its interstellar journey might be sudden or gradual. Perhaps a giant planet migrates outward, its gravity disturbing the orbits of countless small bodies. Perhaps a close encounter with a sibling comet provides just enough gravitational assist to push our comet onto an escape trajectory. Or perhaps the cumulative effect of many small perturbations gradually increases its orbital energy until it exceeds the escape velocity of its star system. However it happens, our comet begins its journey into interstellar space, leaving behind the only home it has ever known, embarking on a voyage that will last longer than its home star will shine. The first million years of interstellar travel would be a period of adjustment. The comet would cool from whatever residual heat it retained from its home system, reaching equilibrium with the cosmic microwave background. Any volatile gases that might have been slowly sublimating in the weak warmth of its distant sun would freeze solid. The last chemical reactions would slow and stop as the temperature approaches absolute zero. The comet would enter a state of suspended animation, its atoms locked in place, its chemistry frozen, its structure preserved as perfectly as if it had been deliberately designed as a time capsule. As our dark comet drifts through interstellar space, it bears witness to the evolution of its galaxy. Stars are born in giant molecular clouds, shine for millions or billions of years, then die in various ways depending on their mass. From the comet's perspective, stars would appear and disappear like fireflies on a summer evening, each stellar lifetime compressed into what would seem like moments. Supernova would flash like distant fireworks, briefly outshining entire regions of the galaxy before fading back to darkness. Planetary nebulae would bloom like flowers, the dying gasps of sun-like stars creating beautiful shells of glowing gas that expand and fade over thousands of years. The comet's path through the galaxy would be complex, influenced by the combined gravity of billions of stars. It might initially travel outward from its birthplace, climbing away from the galactic disk into the halo, where stars are sparse and the darkness is even more profound. Or it might follow a more circular path, staying within the disk but slowly drifting from one spiral arm to another. Over millions of years, the comet would likely pass relatively close to many stars, perhaps coming within a light year or less, but never close enough to be captured or significantly heated. Each close passage would slightly alter its trajectory, sending it off in a new direction, ensuring that its path through the galaxy would be essentially random, unpredictable even in principle. After 100 million years of travel, our comet might find itself in a very different part of the galaxy from where it started. The stars around it would be strangers, formed from different molecular clouds, perhaps with different compositions and ages. If the comet could somehow sense its surroundings, it would notice that the stellar population has changed. The very oldest stars, those formed in the early universe when heavy elements were scarce, would be slowly disappearing, dying off and not being replaced. Younger stars enriched with the ashes of previous generations would be becoming more common. The galaxy itself would be evolving, its spiral arms slowly winding tighter, its overall rotation carrying the comet around the galactic centre. At the billion-year mark, our dark comet would have witnessed profound changes in the galaxy. Entire stellar associations would have formed and dispersed. Massive star-forming regions would have blazed with the light of thousands of young stars, then faded as those stars aged and died or drifted apart. The comet might have passed through several spiral arms, experiencing the slightly denser interstellar medium and increased stellar density. Though even in spiral arms, the space between stars would still be vast and empty by human standards. The background of cosmic rays bathing the comet would have varied as it passed near supernova remnants or through regions of different magnetic field strength, each variation leaving subtle marks in the comet's surface chemistry. The patient accumulation of cosmic ray damage would be one of the few changes our comet would experience during its journey. Each high-energy particle striking the surface would create a tiny cascade of secondary particles, breaking molecular bonds and creating new compounds. Over billions of years, this would create a rind of processed material, perhaps a meter or more thick, chemically different from the pristine interior. This rind would be a record of the comet's journey, with different layers potentially preserving information about different regions of the galaxy the comet had passed through. If the cosmic ray flux was higher in certain regions, those periods would be recorded as layers with more processing, more complex chemistry, more exotic isotope ratios. 5 billion years into its journey, our comet would exist in a galaxy noticeably different from the one where it was born. Many of the stars that existed when it began its journey would have died, their material recycled into new generations of stars and planets. The sun that warmed its birthplace might now be a white dwarf, slowly cooling in space, or perhaps it would have been a massive star that long ago exploded as a supernova, enriching the interstellar medium with heavy elements. The planets that formed alongside our comet, if any survived their star's death, would be frozen worlds orbiting a stellar corpse, or perhaps they would have been destroyed, vaporized when their star expanded into a red giant. Our comet, however, would continue its journey unchanged in any fundamental way. Its core would still preserve the original materials from its formation, atoms that were arranged into molecules 10 billion years ago and have remained in the same configuration ever since. In a universe where everything changes, where nothing remains constant, our dark comet would be an island of stability, a fragment of deep time carrying its message forward into an uncertain future. It would be like a note in a bottle thrown into the ocean, except the ocean is the galaxy, and the journey might last longer than the Earth has existed. The concept of simultaneity becomes meaningless on these timescales. Events that we think of as happening at the same time in different parts of the galaxy are separated by thousands of years at the speed of light. Our comet, travelling much slower than light, would experience an even more extreme dislocation of temporal reference frames. By the time news of an event in one part of the galaxy reached the comet's location, millions of years might have passed since the event occurred. The comet would exist in a temporal bubble, isolated not just in space but in time, carrying its ancient cargo through a galaxy where different regions exist in different epochs from its perspective. As our comet approaches the 10 billion year mark of its journey, the universe itself would have aged significantly. The cosmic microwave background would have cooled slightly, dark energy would have pushed galaxies farther apart, and the overall star formation rate in the universe would have declined. Our galaxy might have experienced close encounters, or even mergers with other galaxies, events that would have dramatically reorganized the stellar population and potentially sent our comet on an entirely new trajectory. Through all of this cosmic evolution, our comet would continue its patient journey, unaffected by the grand changes happening around it, focused, if we can use such a word for an unconscious object, solely on its eternal voyage through the darkness. The question of when such a journey might end is perhaps meaningless. Our comet might eventually encounter another star system and be captured, ending its interstellar wandering. But the odds of this happening are incredibly small. Space is so vast and stars so relatively small that our comet could travel for trillions of years without ever coming close enough to a star to be captured. It might witness the death of all the stars in the galaxy, watching as one by one they exhaust their fuel and fade to darkness. It might still be travelling when the last black holes evaporate through Hawking radiation, when the universe reaches its ultimate heat death, when time itself becomes meaningless because nothing changes anymore. But let's imagine a different fate for our comet. After 10 billion years of travel, it approaches another star, a young sun much like the one it left so long ago. By pure chance, its trajectory brings it close enough to be captured by the star's gravity. It falls inward, slowly at first, then faster as it approaches the warmth it hasn't felt for eons. The ancient ices begin to sublimate, creating a coma for the first time in billions of years. The comet has become visible again, transformed from a dark wanderer into a bright messenger, delivering its cargo of ancient materials to a new stellar system. If this system harbours planets, and if one of those planets has the right conditions for life, our comet might deliver more than just ice and rock. It might deliver complex organic molecules formed in another star system billions of years ago, preserved perfectly through its long journey, now available to participate in the chemistry of a new world. The atoms that were arranged into molecules in a stellar nursery that no longer exists might become part of living organisms on a planet that didn't exist when the comet began its journey. This is the profound possibility that dark comets represent, the transfer not just of matter but of information, of chemical patterns, of the potential for life across distances and times that seem impossible to bridge. The journey through time that dark comets undertake is thus revealed to be not just a passage through space, but a connection between different epochs of cosmic history. Each dark comet is a thread linking the deep past to the far future, carrying messages that were written before their readers existed, delivering gifts from stars that died before their recipients were born. They are the ultimate expression of cosmic patience, of processes that unfold on timescales that dwarf any human conception of duration. Yet that might be fundamental to understanding how the universe evolves and how life might spread through the cosmos. As we contemplate these vast journeys through time, we begin to see our own existence in a different light. We live in a thin slice of cosmic time, a moment so brief that from the perspective of a dark comet we barely exist at all. Yet in our brief moment, we've developed the ability to conceive of these vast timescales, to imagine journeys that last billions of years, to understand processes that unfold over durations that make our entire species' existence seem like a single heartbeat. This is perhaps the most remarkable thing about contemplating dark comets. They remind us that while we are temporary, we are part of something eternal, something that connects all times and all places in the vast tapestry of cosmic evolution. The dark comets, if they exist, are the universe's way of remembering its past and preparing for its future. They're archives of conditions that no longer exist anywhere else, carrying forward information that would otherwise be lost to time. They are seeds that might wait billions of years before finding suitable soil, but when they do, they might bloom into new chemistry, new complexity, perhaps even new life. They are reminders that in the universe, nothing is ever truly lost, that matter and energy and information are constantly being recycled, reformed and redistributed in an eternal dance that began with the Big Bang, and will continue until the universe itself ends, whatever that ending might be. Time, from the perspective of dark comets, is not a river flowing in one direction, but an ocean in which they drift, touching different shores at different epochs, connecting moments separated by eons in ways that we're only beginning to understand. Their journeys through time are not just physical passages through space, but philosophical challenges to our understanding of existence, duration, and the nature of cosmic evolution. They invite us to think on scales that stretch our minds to their limits, to contemplate processes that unfold with a patience that transcends any human experience, and to see ourselves as part of a story that began long before we arrived and will continue long after we're gone. What if these dark wanderers carry materials from distant stellar systems, bearing within their frozen cores elements forged in alien suns long ago extinguished, serving as bridges between stellar islands that seem forever separate in the vast ocean of space? As we continue our contemplation of dark comets, we turn our attention to their potential role as messengers, carriers of information and materials between star systems that would otherwise remain completely isolated from one another. These cosmic ambassadors, if they exist, would represent a form of communication that transcends any technology we might imagine, a natural process that has been connecting different regions of the galaxy since the first stars began ejecting comets into interstellar space billions of years ago. The concept of interstellar messengers isn't entirely new to human thought. We've long imagined sending messages to the stars, from the golden records on the Voyager spacecraft to radio, broadcasts deliberately aimed at nearby star systems. But these efforts are conscious, deliberate attempts at communication, requiring technology and intention. Dark comets, on the other hand, would be unconscious messengers, carrying their cargo without any awareness of their role, delivering materials and information through a process as natural and inevitable as the formation of stars themselves. They would be like seeds blown by the wind, except the wind is the complex gravitational field of the galaxy, and the seeds carry not just the potential for new growth, but actual samples of their parent systems. To understand what kinds of messages these dark comets might carry, we need to consider what makes each star system unique. Every star is born from a collapsing cloud of gas and dust, but no two clouds are exactly alike. They differ in their chemical composition, reflecting the history of stellar evolution in their region of the galaxy. They differ in their density and temperature, which affects how stars and planets form within them. They differ in their exposure to external influences like nearby supernova, stellar winds from massive stars, and the ultraviolet radiation that permeates different regions of space. All of these differences are recorded in the materials that condense from these clouds, including the comets that form in the outer regions of emerging planetary systems. A dark comet from a star system that formed near a recent supernova would carry distinctive isotopic signatures, ratios of different atomic varieties that could only be produced in the extreme conditions of an exploding star. These isotopes would be incorporated into the comet's ice and dust during its formation, preserved through its long interstellar journey, and potentially delivered to another star system millions or billions of years later. Scientists in that distant system, if they were advanced enough to study the comet's composition, could read its isotopic signatures like a cosmic postmark, determining not just that the comet came from another star, but potentially identifying characteristics of its parent system and the conditions under which it formed. The organic chemistry preserved in dark comets would be particularly fascinating as a form of interstellar message. Different star systems might produce different suites of organic molecules, depending on the temperature and radiation environment where comets formed, the presence of catalytic minerals, and the specific mix of elements available. A comet from a carbon-rich system might carry complex carbon chains and aromatic molecules that would be rare in a carbon-poor system. A comet that formed in the presence of strong ultraviolet radiation might carry molecules that were processed into forms that wouldn't naturally occur in a more shielded environment. Each dark comet would thus carry a chemical fingerprint of its home system, a sample of the organic chemistry that was possible under those particular conditions. But the messages carried by dark comets wouldn't just be about their origins, they would also be about their journeys. As we discussed earlier, the surface of a dark comet would be processed by cosmic rays during its interstellar voyage, creating new compounds and altering isotope ratios. This processing would create a kind of travel log, a record of the different environments the comet passed through. Regions of the galaxy with higher cosmic ray flux would leave different signatures than quieter regions. Passages near neutron stars or black holes might create distinctive patterns of radiation damage. Close encounters with molecular clouds might deposit thin layers of interstellar dust on the comet's surface. All of these experiences would be written in the comet's chemistry, creating a multi-layered message about both where it came from and where it had been. The possibility that dark comets might carry biological or pre-biological materials adds another dimension to their role as messengers. Life, as we understand it, is incredibly good at creating complex information-rich molecules. DNA and RNA are essentially molecular libraries, storing vast amounts of information in their sequences of nucleotide bases. Proteins are molecular machines, their structures encoding information about function and process. If life existed in a dark comet's parent system, even just simple microbial life, some of its molecular machinery might be incorporated into comets forming in that system. These biological molecules would be preserved in the comet's ice, potentially viable after billions of years in the deep freeze of interstellar space. This raises the profound possibility of panspermia, the idea that life might spread through the galaxy not through deliberate colonization, but through the natural exchange of materials between star systems. A dark comet, carrying microbial life or complex biological molecules from one system to another, wouldn't just be delivering materials. It would be delivering information, patterns, templates for a molecular organization that could influence the development of life in its destination system. This wouldn't be evolution in the traditional sense, but a kind of cosmic cross-pollination, where biological innovations that arose in one system could be shared with others across vast distances and times. Even if dark comets don't carry actual life, they might carry the chemical precursors that make life more likely to arise. Amino acids, the building blocks of proteins, have been found in meteorites and are thought to form naturally in space. Nucleotide bases, the letters of the genetic alphabet, can also form through natural chemical processes. If dark comets concentrate and preserve these molecules, delivering them to young planets where conditions are suitable for life, they might significantly increase the probability of life arising. In this view, dark comets would be like cosmic gardeners, seeding planets with the ingredients for life, even if they don't carry life itself. The timing of when dark comets deliver their messages would be crucial. A comet arriving at a young star system while planets are still forming might have its materials incorporated directly into growing planets, becoming part of their original composition. A comet arriving later, impacting a fully formed planet, might deliver its materials to the surface, where they could participate in surface chemistry or be incorporated into any existing biology. The same message, the same collection of materials and information, might have completely different effects depending on when it's delivered, like a letter that changes meaning depending on when it's read. The sheer number of potential messengers is staggering to contemplate. If each star system in our galaxy has ejected millions of comets over its lifetime, and there are hundreds of billions of star systems, then the number of dark comets drifting through interstellar space could be in the hundreds of trillions or even quadrillions. Each one would be a unique message, a distinct sample of materials and conditions from its parent system. The galaxy would be filled with these messages, crossing in the darkness, occasionally delivering their cargo to new systems, but mostly continuing their eternal journeys, patient messengers waiting for recipients that might never come. The idea that we might be surrounded by messages from other stars, encoded not in radio waves or laser pulses, but in the chemistry of dark comets, transforms our perspective on the search for extraterrestrial intelligence. We've been listening for deliberate signals, looking for evidence of technological civilizations trying to communicate, but perhaps nature itself has been communicating all along, sending messages between star systems through these dark wanderers. These wouldn't be messages in any conventional sense, not attempts at communication, but they would be information-rich samples that could tell us about conditions in other star systems, about the chemistry possible in different environments, perhaps even about life that might exist elsewhere in the galaxy. Our own solar system has likely received many such messages over its history. Every interstellar comet that has been captured by our sun's gravity, every one that has impacted our planets, has delivered materials from another star system. Earth itself might have received dozens or hundreds of such impacts over its history, each one potentially delivering exotic materials, unusual isotopes, or complex organic molecules. Some scientists have suggested that Earth's water might have been delivered by comets, though most now think asteroids were the primary source. But what if some fraction of Earth's water came not from comets that formed in our solar system, but from dark comets that formed around other stars? We might literally be drinking water molecules that were frozen in ice around an alien sun billions of years ago. The Moon, with its lack of atmosphere and geological activity, would be an ideal place to search for evidence of past dark comet impacts. Materials delivered to the lunar surface would be preserved for billions of years, potentially maintaining their distinctive isotopic and chemical signatures. Future lunar missions might specifically look for anomalous materials that could indicate an interstellar origin, searching for messages that were delivered to the Earth-Moon system long before humans evolved to read them. Each discovery of interstellar material would be like finding a letter from another star, a tangible connection to a distant place and time. Mars, too, might preserve evidence of dark comet impacts. Its thin atmosphere and cold, dry conditions would help preserve organic molecules and other materials delivered from space. The layered deposits in Mars's polar caps might contain a record of impacts over millions of years, potentially including materials from interstellar comets. As we continue to explore Mars with increasingly sophisticated rovers and eventually human missions, we might discover that the red planet has been collecting messages from other stars, preserving them in its rocks and ice, waiting for us to develop the technology to read them. The outer solar system, particularly the moons of Jupiter and Saturn, might be especially rich in materials delivered by dark comets. These moons are far enough from the Sun that captured interstellar comets might survive longer before sublimating away. Europa's subsurface ocean, Enceladus's geysers, and Titan's hydrocarbon lakes might all contain materials that originated in other star systems, delivered by dark comets over the age of the solar system. Future missions to these worlds might discover that they're not just interesting for their potential to harbour life, but also as collectors of interstellar messages, libraries of materials from across the galaxy. The philosophical implications of dark comets as messengers are profound. If materials are constantly being exchanged between star systems, then the traditional view of stellar systems as isolated islands needs to be reconsidered. Instead, we might think of the galaxy as a vast network, with dark comets serving as the connections between nodes. Information, in the form of chemical patterns and isotopic signatures, would flow through this network, creating a kind of galactic communication system that operates without any conscious intent or technological infrastructure. It would be communication in the deepest sense, the sharing of information across space and time, but happening through natural processes rather than deliberate signals. This natural communication system would have characteristics very different from any technological communication we might imagine. The messages would travel slowly, taking millions or billions of years to go from sender to receiver. There would be no way to aim messages at specific targets. They would be broadcast in all directions, reaching whatever stars happened to be in their path. There would be no way to recall or update messages once sent. They would carry their information unchanged through the eons, and there would be no conversation, no back and forth exchange. Each message would be a one-way transmission from past to future. Yet despite these limitations, or perhaps because of them, dark comets as messengers would have a kind of reliability and permanence that technological communication lacks. Radio signals fade with distance and can be disrupted by interference. Laser beams require precise aim and can be blocked by intervening matter. But a dark comet, once launched on its journey, will continue travelling for billions of years, carrying its message through any obstacle, patient and persistent in a way that no technological system could match. The message might never be received, but it will never be lost either, continuing its journey as long as the universe exists. The role of dark comets as messengers also raises questions about our own solar system's contributions to this galactic communication network. Our Sun has likely ejected millions of comets over its history, sending them on interstellar journeys that might eventually take them to other stars. These comets would carry information about our solar system, samples of our chemistry, perhaps even traces of Earth's biology, if any materials from our planet were incorporated into comets through impacts or other processes. We are not just receivers of interstellar messages, but senders as well, unconsciously broadcasting information about our corner of the galaxy to unknown recipients in the distant future. Some of these messages from our solar system might be special. Comets ejected after life arose on Earth might carry organic molecules or even microorganisms that originated on our planet. If Earth life is unique or rare in the galaxy, these comets would be carrying particularly valuable cargo, seeds that might take root in other systems under the right conditions. We might be, without knowing it, the source of life for worlds that won't form for billions of years, around stars that don't yet exist. This is a kind of immortality, not for individuals or even species, but for the patterns and processes of life itself, preserved in ice and carried between the stars by dark messengers. The search for dark comets and the messages they might carry is just beginning. As our detection capabilities improve, we might soon be able to identify dark comets passing through our solar system, to capture samples from them, to read the messages they've been carrying through space for eons. Each discovery would be a window into another place and time, a tangible connection to the wider galaxy. We might learn about stellar systems very different from our own, about chemistry that doesn't occur naturally in our neighbourhood, about the diversity of conditions and processes in the galaxy. But perhaps the most important message carried by dark comets is not in their chemistry, but in their very existence. They would be proof that the galaxy is more connected than we imagined, that isolation is an illusion, that every star system is part of a vast network of material and information exchange. They would show us that we are not alone, not because there are other civilizations sending us signals, but because we are all, every star and planet and comet, part of the same galactic ecosystem, sharing materials and information through natural processes that have been operating since the galaxy was young. In the cold between stars, chemistry becomes something strange and wonderful, a realm where the normal rules of molecular interaction are suspended, where time nearly stops, and where processes that would be impossible under the warm influence of starlight can unfold with patient precision. The chemistry of dark comets represents one of the most fascinating aspects of these hypothetical objects, a natural laboratory where exotic compounds might form, where the building blocks of life could be assembled and preserved, and where the universe conducts experiments in molecular organization that we're only beginning to understand. This chemistry of darkness isn't just about the absence of light and heat. It's about the unique conditions that exist in the vast spaces between stars, conditions that might be essential for understanding how complex molecules spread through the galaxy, and how life's ingredients might be distributed across cosmic distances. The temperature in interstellar space, hovering just 2.7 degrees above absolute zero, creates a chemical environment unlike anything we can easily replicate on Earth. At these temperatures, even the most volatile substances are frozen solid, locked into crystalline matrices that can preserve molecular structures for billions of years. But this isn't a static, unchanging environment. Cosmic rays provide a constant, if weak, source of energy, breaking some molecular bonds while enabling the formation of others. The result is a kind of slow-motion chemistry, where reactions that would occur in microseconds at room temperature might take millions of years, but where the products of these reactions are immediately frozen in place, prevented from decomposing or reacting further. Consider what happens to water ice, the primary component of most comets, in these conditions. On Earth, we think of ice as a simple, stable solid, but in the extreme cold of interstellar space, water ice can exist in various exotic forms. There's amorphous ice, a glassy form with no regular crystal structure, which can trap other molecules within its disordered matrix like insects in amber. There's cubic ice, with a different crystal structure than the hexagonal ice we're familiar with on Earth. These different forms of ice have different properties, different abilities to preserve and protect other molecules, different ways of interacting with cosmic radiation. A dark comet might contain layers of different ice types, each formed under slightly different conditions, each preserving a different chapter in the comet's chemical history. Within this ice matrix, a complex chemistry can unfold, driven by the energy from cosmic rays. When a high-energy particle strikes the ice, it creates a cascade of secondary particles and photons, briefly heating a tiny region to temperatures where chemical reactions can occur. For a fraction of a second, molecules can move, bonds can break and reform, new compounds can be created. Then the cold reasserts itself, freezing the products of these reactions in place before they can decompose. Over millions of years, this process, called radiolysis, can transform simple molecules into complex ones, building up a reservoir of organic compounds that wouldn't exist without the unique conditions of interstellar space. Laboratory experiments have given us glimpses of what this chemistry might produce. When scientists expose simple ice mixtures to radiation at very low temperatures, mimicking the conditions in interstellar space, they observe the formation of remarkably complex molecules. Amino acids, the building blocks of proteins, form spontaneously. Sugars, including ribose, a key component of RNA, can be created. Even nucleotide bases, the letters of the genetic code, have been synthesized in these experiments. If such complex chemistry can occur in laboratory experiments lasting just days or weeks, Imagine what might be possible in a dark comet over billions of years of cosmic ray exposure. The presence of dust grains within the ice adds another dimension to this chemistry. These grains, typically made of silicates or carbon compounds, can act as catalysts, providing surfaces where molecules can meet and react more easily than they would in pure ice. The grains might also protect some molecules from radiation, while exposing others, creating gradients of chemical processing within the comet. Some grains might be magnetic, creating tiny magnetic fields that could influence the chemistry of charged molecules and radicals. Each grain would be like a tiny chemical factory, producing its own unique suite of compounds depending on its composition and local environment. The chemistry of darkness also involves the preservation of highly reactive species that couldn't exist under normal conditions. Free radicals, molecules with unpaired electrons that would instantly react with other molecules at Earth temperatures, can remain stable for millions of years in the cold of interstellar space. These radicals build up to concentrations that would be impossible to achieve in any terrestrial laboratory, creating a reservoir of chemical potential energy. If a dark comet carrying such radicals were to warm up, perhaps by entering another star system, these radicals could suddenly become reactive, driving a burst of chemistry that could synthesize complex molecules in ways we've never observed. The isotopic chemistry of dark comets would be particularly interesting. Different isotopes of the same element can behave slightly differently in chemical reactions, especially at very low temperatures, where quantum effects become important. Over billions of years, these slight differences could lead to isotopic enrichments or depletions in certain molecules, creating signatures that would indicate not just that a molecule formed in interstellar space, but potentially how long it spent there and what kinds of processing it experienced. These isotopic signatures would be like timestamps, recording when and where different chemical processes occurred. One of the most intriguing aspects of dark comet chemistry is the possibility of autocatalytic reactions, chemical processes that produce compounds that catalyze their own formation. Such reactions are thought to be important in the origin of life, as they can lead to the rapid production of specific molecules once a critical threshold is reached. In the slow-motion chemistry of a dark comet, autocatalytic networks might develop over millions of years, gradually building up concentrations of self-reinforcing chemical systems. These wouldn't be alive in any sense, but they would represent a level of chemical organization that bridges the gap between simple molecules and the complex chemistry of life. The role of quantum effects in dark comet chemistry is something we're only beginning to explore theoretically. At temperatures near absolute zero, quantum tunneling becomes important, allowing chemical reactions to occur even when there isn't enough thermal energy to overcome activation barriers. Molecules can tunnel through energy barriers rather than going over them, enabling reactions that would be impossible at any temperature high enough to provide classical thermal activation. This quantum chemistry might produce molecules and molecular arrangements that don't exist anywhere else in the universe, unique products of the extreme conditions in interstellar space. The compartmentalization of chemistry within dark comets could lead to fascinating complexity. Different regions of the comet might have different chemical compositions depending on when and how they formed. Layers deposited at different times might preserve different chemical environments. Cracks and voids in the comet's structure might create isolated chambers where unique chemistry could develop. Over billions of years, a dark comet might develop into a complex heterogeneous chemical system with different regions containing different suites of molecules, different reaction networks, different frozen chemical potentials waiting to be released. The interaction between organic and inorganic chemistry in dark comets could produce particularly interesting results. Organic molecules might form complexes with metal ions from dust, grains, creating organometallic compounds that could serve as catalysts for further reactions. Clays and other minerals might provide templates for the organization of organic molecules, potentially creating primitive versions of the mineral-organic interactions that are crucial to life on Earth. The boundary between ice and mineral grains might be especially rich in chemical diversity, with gradients of composition and reactivity that could drive the formation of complex molecular systems. Photochemistry, driven not by starlight but by the faint ultraviolet radiation that permeates interstellar space and the brief flashes of light from cosmic ray interactions, would add another layer to dark comet chemistry. Certain molecules are particularly sensitive to ultraviolet light, breaking apart or rearranging when exposed to even weak radiation. Over billions of years, this slow photochemistry could transform the molecular inventory of a dark comet, creating products that depend not just on the starting materials, but on the entire radiation history of the comet's journey. Different wavelengths of radiation would drive different reactions, creating a complex interplay between the comet's chemistry and the radiation environment of interstellar space. The possibility of polymer formation in dark comets is particularly intriguing from an astrobiological perspective. Polymers, long chains of repeated molecular units, are essential to life as we know it. Proteins are polymers of amino acids, DNA and RNA are polymers of nucleotides, and many other biological molecules are polymeric in nature. In the cold of interstellar space, with cosmic rays providing activation energy and billions of years available for reactions to proceed, simple monomers might link together into chains. These polymers would be immediately frozen in place, preserved from degradation, potentially accumulating to significant concentrations over cosmic time. The role of dark comets in the cosmic carbon cycle deserves special attention. Carbon is the backbone of organic chemistry, and its various forms from simple molecules like carbon monoxide and carbon dioxide to complex organics would all be present in dark comets. The transformation between these different forms, driven by cosmic ray chemistry and quantum processes, would represent a kind of carbon chemistry that doesn't occur anywhere else. Dark comets might be the universe's primary means of processing carbon, from simple to complex forms, creating the molecular diversity that makes carbon chemistry so rich and varied. Water, the most abundant component of most comets, plays a crucial role in this chemistry, not just as a passive matrix but as an active participant. Water molecules can be split by radiation into hydrogen hydroxyl radicals, which can then react with other molecules to create new compounds. The hydrogen can reduce oxidized compounds, while the hydroxyl can oxidize reduced ones, creating a redox chemistry that could drive the formation of complex molecules. The products of water radiolysis could react with carbon compounds to create alcohols, acids, and other oxygenated organics that are important in biological chemistry. The preservation of chemical information in dark comets is remarkable. Unlike planets, where geological activity, weather, and biology constantly recycle and transform materials, dark comets would preserve their chemistry essentially unchanged for billions of years. Each layer would be a snapshot of the chemical conditions when it formed. Each grain would maintain its original composition. Each molecule would remain in the configuration it adopted when the temperature dropped below the point where reactions could occur. This makes dark comets not just chemical laboratories, but chemical libraries, archives of reactions and processes that occurred in the distant past. The potential for chirality, the handedness of molecules that's crucial to biology, adds another fascinating dimension to dark comet chemistry. Life on Earth uses only left-handed amino acids and right-handed sugars, a selectivity that might have originated in space. Circularly polarized light from neutron stars, magnetic fields acting on cosmic rays, or even the weak nuclear force could create slight excesses of one chiral form over another in the molecules forming in dark comets. Over billions of years, these slight excesses could be amplified through autocatalytic processes, potentially creating reservoirs of chirally pure compounds that could seed the emergence of homochiral life on planets. The chemistry of darkness isn't just about what reactions occur, but also about what reactions don't occur. In the warm, energetic environment of a planet or the inner solar system, many molecules are unstable, quickly decomposing or reacting with other compounds. But in the cold of interstellar space, even thermodynamically unstable molecules can persist indefinitely, frozen in place before they can decompose. This means dark comets could carry molecules that we've never observed because they can't exist under the conditions we're familiar with. Exotic compounds that might have unique properties or reactivities if they ever encountered suitable conditions. The surface chemistry of dark comets would be particularly complex, representing the interface between the comet and interstellar space. This surface would be constantly bombarded by cosmic rays, creating a layer of highly processed material. But it would also be the site where new molecules from the interstellar medium could be captured and incorporated into the comet. Hydrogen molecules, the most abundant component of interstellar space, might slowly diffuse into the surface, reacting with radicals to create new compounds. Dust grains from the interstellar medium might occasionally stick to the surface, adding new catalytic sites and new raw materials for chemistry. As we contemplate the chemistry of darkness, we begin to see dark comets not as inert chunks of ice and rock, but as dynamic chemical systems, constantly evolving even as they appear frozen in time. They would be repositories of chemical potential, storing energy in the form of unstable molecules and reactive radicals, preserving information in the form of complex molecular structures and isotopic patterns, and serving as bridges between the simple chemistry of the early universe and the complex chemistry that makes life possible. The chemistry of darkness reveals itself to be not an absence but a presence, not a void but a fullness of possibility, waiting in the cold between the stars. Could these dark travellers have seeded life across the cosmic garden, carrying within their frozen hearts not just the raw materials, but perhaps the very templates of existence itself, connecting distant worlds through invisible threads of chemical and possibly biological inheritance? As we approach the deeper implications of dark comets for our understanding of life in the universe, we enter territory that bridges science and philosophy, observation and speculation, the known and the unknowable. The possibility that life might travel between stars preserved in the ice of dark comets transforms our perspective on our own origins and our place in the cosmic story. This isn't just about the mechanics of panspermia, the transfer of life between worlds, but about the profound interconnectedness it implies. The idea that life anywhere might be related to life everywhere, that we might all be part of a single galaxy-spanning phenomenon that transcends individual planets or star systems. The journey of life through space, if it occurs, would be unlike any migration we're familiar with on Earth. It wouldn't be a purposeful journey, with organisms seeking new homes, but an accidental diaspora, with life hitchhiking on cosmic debris, unaware of its voyage, preserved in ice for millions or billions of years, waiting for the chance encounter with a suitable world where it might awaken and flourish once again. This would be evolution on a galactic scale, with natural selection operating not just within ecosystems on individual planets, but across the vast spaces between stars, favouring organisms capable of surviving the extreme conditions of space travel and the shock of arrival on a new world. To understand how life might survive such a journey, we need to consider what we've learned about extremophiles, organisms on Earth that thrive in conditions that would kill most life. We've found bacteria living in the cores of nuclear reactors, archaea thriving in boiling acid, microorganisms surviving in the deepest ocean trenches and the driest deserts. Some organisms can survive being completely desiccated, entering a state called cryptobiosis where all metabolic activity ceases, yet they can revive when water becomes available again, even after years of dormancy. Others can withstand radiation doses thousands of times higher than what would kill a human, their DNA repair mechanisms so efficient that they can reconstruct their genomes even after massive damage. These extremophiles give us a glimpse of what might be possible for life travelling through space in dark comets. Organisms frozen in ice wouldn't need to actively survive the journey. They would simply need to remain viable, their molecular machinery intact enough to restart when conditions become favourable again. The cold of interstellar space would actually help preserve them, slowing all degradation processes to near zero. The ice would shield them from the worst of the cosmic radiation, and even if their DNA were damaged, the repair mechanisms that evolution has crafted over billions of years might be able to fix the damage once the organisms thawed and became active again. But the implications go beyond simple survival. The conditions within a dark comet, with their slow chemistry and long timescales, might actually allow for a kind of evolution to occur even during the journey. Not biological evolution in the traditional sense, but chemical evolution, with complex molecules gradually forming and interacting, potentially creating new arrangements, new possibilities for life. When such a comet delivered its cargo to a new world, it might be delivering not just preserved life, but life that had been transformed by its journey, carrying new chemical innovations that arose during its time in interstellar space. The timing of life's arrival on a planet would be crucial. A world needs to be ready for life, with liquid water, appropriate temperatures, and the right chemical environment. Too early, and the planet might still be molten from its formation. Any delivered organisms instantly vaporized. Too late, and the planet might have already developed its own life, with established ecosystems that would outcompete any arriving organisms. But in that sweet spot, when a planet has cooled enough for liquid water but hasn't yet developed indigenous life, arriving organisms would find a blank canvas, an entire world of resources and no competition, an opportunity for explosive diversification and evolution. This raises profound questions about life on Earth. Did life originate here, arisen from non-living chemistry through abiogenesis, or did it arrive from elsewhere, carried by comets or meteorites. The speed with which life appeared on Earth, seemingly as soon as conditions became suitable, has long puzzled scientists. The oldest evidence for life on Earth dates back nearly 4 billion years, remarkably soon after the planet cooled enough to have liquid water. This rapid appearance might make more sense if life didn't have to originate from scratch, but arrived ready-made, preserved in ice, waiting for the right conditions to resume its existence. The chemical signatures we find in Earth's earliest life forms might hold clues to their ultimate origin. All life on Earth shares certain fundamental features: the use of DNA and RNA for information storage, the same genetic code, the same chirality of biological molecules, the same basic metabolic pathways. This unity might suggest a single origin, but where did that origin occur? If life arrived on Earth via dark comets, these universal features might reflect not the conditions on early Earth, but the conditions in some other star system, perhaps one that no longer exists, its star having died billions of years ago while its life continues here. The possibility of life travelling via dark comets also has implications for the search for life elsewhere in the universe. If life can spread between star systems, then finding life on Mars or Europa or Enceladus wouldn't necessarily mean that life originated independently in multiple places in our solar system. It might all be related, sharing a common origin, whether that origin was Earth, Mars, or somewhere else entirely. This would be both exciting and slightly disappointing, evidence that life can spread and survive in multiple environments, but not evidence for independent origins of life. On a galactic scale, dark comets as carriers of life would create a kind of biological network, with life slowly spreading from star to star like a vast, slow infection. Not infection in a negative sense, but in the sense of life taking hold wherever conditions allow, spreading from initial points of origin to fill all available niches. Over billions of years, life might have spread throughout large regions of the galaxy, creating a galactic biosphere where life on different planets shares deep evolutionary relationships, even if those planets are separated by hundreds or thousands of light years. This galactic biosphere wouldn't be uniform. The vast distances and times involved would ensure that life evolving on different planets would diverge dramatically, adapting to local conditions, exploring different evolutionary pathways. Life that originated from the same source might become unrecognizably different after billions of years of separate evolution. Yet at the molecular level, in the fundamental chemistry of life, similarities might persist, fossil evidence of shared ancestry that could be detected with sufficiently advanced analysis. The role of dark comets in seeding life would also depend on the frequency of suitable planets. If Earth-like planets are rare, then most dark comets carrying life would never find suitable homes, continuing their journeys forever through the void, carrying their frozen cargo to no purpose. But if suitable planets are common, as recent exoplanet discoveries suggest they might be, then the galaxy could be teeming with life, all of it related through the exchange of materials via dark comets, a vast family of life separated by unimaginable distances, but connected through shared chemistry and history. The implications extend to the future of life as well. Earth won't remain habitable forever. In about 1 billion years, the sun's increasing luminosity will trigger a runaway greenhouse effect, boiling away the oceans and ending life as we know it. But by then, countless comets carrying Earth life might have been ejected into interstellar space, carrying the legacy of our biosphere to other stars. Life that originated on Earth, or at least life that passed through Earth on its galactic journey, might continue elsewhere, evolving in directions we can't imagine, perhaps eventually developing intelligence and wondering about their own origins, never knowing that part of their history traces back to a long-dead world, orbiting a star that has swollen into a red giant. The preservation of life in dark comets might also represent a kind of cosmic backup system, ensuring that life, once started, is very difficult to completely eradicate. Even if a gamma-ray burst sterilized an entire region of the galaxy, life preserved in dark comets already in interstellar space would survive, ready to reseed worlds once conditions improved. Even if all the planets in a stellar system were destroyed, comets carrying life from that system might already be on their way to other stars. Life, in this view, would be incredibly resilient on a galactic scale, able to survive catastrophes that would destroy individual worlds or even entire stellar systems. The chemical evolution that might occur within dark comets during their journeys adds another layer of complexity to life's cosmic journey. The slow, radiation-driven chemistry we discussed earlier might not just preserve life, but transform it, creating new molecules, new possibilities for biological organization. A dark comet might start its journey carrying simple bacteria and arrive at its destination with a complex chemical ecosystem, a soup of organic molecules and possibly still viable organisms that had been slowly cooking for billions of years. This wouldn't be evolution through reproduction and natural selection, but a kind of chemical evolution, with molecules competing for resources and stability within the comet's ice matrix. The delivery mechanism for life would be as important as its preservation. A dark comet entering a star system would begin to warm as it approached the star, potentially releasing volatile compounds and creating a temporary atmosphere around itself. If it impacted a planet, the energy of impact might vaporize much of the comet, but some material would survive, especially if the comet broke up in the atmosphere and pieces fell as a gentler rain rather than a single catastrophic impact. The delivered organisms would need to survive not just the journey, but the arrival, adapting quickly to their new environment or perishing. The possibility that dark comets might deliver not just life but entire ecosystems is particularly intriguing. A large comet might contain different types of organisms in different regions, preserved from some ancient planetary biosphere. Upon delivery to a new world, these organisms might reconstitute complex ecological relationships, predators and prey, producers and decomposers, all arriving together like colonists with everything they need to establish a new settlement. This would dramatically accelerate the development of complex ecosystems on newly habitable worlds, jump-starting biological evolution with a complexity that might otherwise take billions of years to develop. The search for evidence of life delivered by dark comets is challenging, but not impossible. We might look for biological molecules in unusual places, like the lunar surface where ancient comet impacts would be preserved, or in the oldest rocks on Earth, searching for chemical signatures that predate Earth's own biological history. We might analyze the genomes of Earth organisms, looking for genes or gene families that seem oddly out of place, possibly inherited from organisms that evolved elsewhere. We might study the biochemistry of extremophils, looking for adaptations that make more sense as preparations for space travel than for any Earth environment. The philosophical implications of life travelling via dark comets are profound. If life spreads naturally through the galaxy, then the emergence of life on any particular planet becomes less special but more connected to the cosmic whole. We would be part of a galactic phenomenon, a widespread flowering of chemistry into biology that transcends individual worlds. The questions of "are we alone?" and "where did we come from?" would have different answers than we might expect. We might not be alone, but our cosmic siblings might be so distant and so different that we'd never recognize our kinship. We might have come from Earth, but Earth life itself might have come from elsewhere, making us all immigrants in a cosmic sense. The responsibility that comes with this possibility is sobering. If Earth life might spread to other worlds via ejected comets, then we are not just stewards of our own planet, but potential seeds for life elsewhere. The extinction of species on Earth might mean the loss of biological innovations that could have flourished on other worlds millions of years in the future. Our actions here and now might have consequences that ripple across the galaxy over geological time, affecting the development of life on worlds we'll never see, around stars that haven't yet formed. As we contemplate these implications, we see that dark comets represent more than just a mechanism for moving materials between stars. They might be the threads that weave life into a galactic tapestry, connecting distant worlds in a web of biological relationship that spans space and time. They might be the universe's way of ensuring that life, once started, spreads and persists, filling every possible niche, exploring every possible form, creating a cosmic garden of unimaginable diversity and beauty. The journey of life through the cosmos, carried by dark comets, would be the ultimate expression of life's resilience and creativity, its ability to transcend the boundaries that seem absolute, to make the impossible journey from star to star, carrying the spark of existence through the cold darkness to kindle new fires wherever conditions allow. As we return from our journey through the possibility of dark comets, the mystery deepens rather than resolves, like looking into a clear pool of water only to discover it has no bottom, extending down into depths our lights cannot penetrate. The universe keeps its secrets while inviting us to wonder and dream, offering glimpses of vast processes that might be fundamental to cosmic evolution, while withholding the definitive proof that would transform speculation into certainty. In not knowing, we find a peace that certainty could never provide, a sense of ongoing discovery that makes our existence in this cosmos an eternal adventure rather than a solved puzzle. The dark comets, whether real or imagined, remind us of the vastness we inhabit, the scales of space and time that dwarf our human experience while somehow still including us in their grand narrative. Throughout our exploration, we've contemplated objects that might not exist, or might exist in numbers beyond imagination, drifting through the darkness between stars like an invisible river of ice and rock and possibility. We've considered how they might form, how they might evolve during journeys lasting billions of years, what they might carry within their frozen hearts, and what their existence might mean for our understanding of life and our place in the universe. But at the end of this contemplation, we're left not with answers but with deeper questions, not with certainty but with wonder, not with conclusions but with invitations to continue exploring, continue questioning, continue marvelling at the cosmos we're privileged to inhabit. The beauty of the dark comet mystery lies partly in its resistance to easy resolution. Unlike some scientific questions that can be answered with a single observation or experiment, The question of dark comets touches on so many aspects of astronomy, chemistry, biology, and cosmology that fully understanding them would require advances in multiple fields. We would need to detect them directly, which requires technology we're only beginning to develop. We would need to sample them, which requires space missions we're only beginning to imagine. We would need to understand their chemistry, which requires laboratory techniques and theoretical frameworks we're only beginning to create. Each advance brings new questions, each answer reveals new mysteries, each discovery shows us how much more there is to discover. This resistance to easy answers is not a frustration, but a gift. In a universe where everything was known, where every question had a definitive answer, there would be no room for wonder, no space for imagination, no reason to look up at the night sky with awe. The mystery of dark comets, like all the great mysteries of science, keeps us humble while inspiring us to reach further. It reminds us that for all our knowledge, for all our sophisticated instruments and theories, we're still children exploring a vast house, having mapped only a few rooms while entire wings remain undiscovered, their doors closed, their contents unknown but somehow sensed, calling to us through our curiosity and wonder. Consider what we've learned just by contemplating the possibility of dark comets. We've expanded our perspective on the connectedness of the galaxy, seeing stellar systems not as isolated islands, but as nodes in a vast network of material exchange. We've deepened our appreciation for the chemistry that occurs in the cold darkness of space, recognizing that absence of heat and light doesn't mean absence of activity, but rather enables different kinds of processes that might be crucial for cosmic evolution. We've broadened our understanding of how life might spread through the universe, not necessarily through deliberate colonization or technological communication, but through natural processes that operate on scales we're only beginning to appreciate. Even if dark comets don't exist in the numbers we've imagined, even if the spaces between stars are emptier than our speculation suggests, the exercise of contemplating them has value. It's pushed us to think about extreme preservation, about chemistry at the edge of absolute zero, about connections across distances that seem impossible to bridge. It's made us consider our own solar system's history differently, wondering what visitors might have passed through, what materials might have been delivered or removed, what influences might have shaped the evolution of our planets and possibly our life. It's invited us to see ourselves as part of something larger, not isolated on our single world, but connected to the entire galaxy through threads we're only beginning to perceive. The search for dark comets is already yielding unexpected discoveries. The detection of Oumuamua and 2I/Borisov proved that interstellar objects do pass through our solar system, validating at least part of the dark comet hypothesis. The growing catalogue of exoplanets shows us that planetary systems are diverse and dynamic, with processes that could easily eject comets into interstellar space. The discovery of complex organic molecules in space tells us that the chemistry we imagine occurring in dark comets does happen, even if we haven't yet found the comets themselves. Each of these discoveries is like finding a piece of a vast puzzle, not enough to see the whole picture, but enough to know that there is a picture, that the pieces do fit together in some grand pattern we're slowly uncovering. The technological advances driven by the search for dark comets and other faint objects will have benefits beyond astronomy. Better detectors, more sophisticated data analysis techniques, improved models of orbital dynamics, all of these, have applications in other fields. The quest to understand these cosmic wanderers pushes us to innovate, to create new tools and techniques that expand our ability to observe and understand not just space, but many aspects of our world. The mystery of dark comets is thus productive, generating progress even as it resists solution, driving us forward even as it recedes before us like a horizon we can approach but never reach. The philosophical implications of dark comets continue to ripple outward as we contemplate them more deeply. If the galaxy is filled with these invisible messengers, then every star system has a history that extends beyond its own formation, incorporating materials and perhaps even life from distant sources. The story of any planet, including Earth, becomes not an isolated narrative but a chapter in a vast galactic epic, with characters and plot elements arriving from other chapters, other stories, creating a complex weave of cause and effect that spans billions of years and thousands of light years. We are all, in this view, products not just of our local conditions but of galactic processes, cosmic citizens whether we recognize it or not. The question of consciousness and observation adds another layer to the mystery. Dark comets, if they exist, have been travelling through space for billions of years unobserved, at least by any consciousness we know of. They've been carrying out their patient journeys, their slow chemistry, their preservation of ancient materials, all without any witness, any awareness, any appreciation of their role in cosmic evolution. But now, through our speculation and search, we're bringing them into consciousness, making them part of the observed universe, giving them meaning through our contemplation. In a sense, we're completing their journey, providing the awareness that gives significance to their billions of years of travel. This raises profound questions about the nature of scientific discovery and human consciousness. Are we discovering dark comets? Or are we creating them through our observation and speculation? Not creating them physically, of course, but creating them as meaningful objects, as parts of the cosmic story that matter because we've recognized their possible importance. This is not to say that dark comets don't exist independently of our awareness of them, but rather that their significance, their meaning in the cosmic narrative, emerges through the interaction between their objective existence and our subjective contemplation of them. The temporal aspects of the dark comet mystery continue to fascinate. These objects, if they exist, operate on timescales that make them bridges not just between different places, but between different epochs. A dark comet arriving in our solar system today might have left its parent system before Earth formed, carrying information about conditions in the galaxy billions of years ago. It would be a messenger from deep time, a tangible connection to eras we can otherwise only infer from the light of distant galaxies and the cosmic microwave background. The possibility of directly sampling such ancient material, of holding in our hands atoms that have been travelling through space since before our sun was born, is both humbling and exhilarating. The future of dark comet research holds tremendous promise. New telescopes, both ground-based and space-based, will have unprecedented sensitivity, potentially able to detect the faint heat signatures or gravitational influences of dark comets passing through our solar system. Missions to the outer solar system might encounter captured interstellar objects, providing opportunities for direct sampling. Advanced computer simulations will better model the formation and evolution of cometary populations, predicting where and how dark comets might be found. Each advance brings us closer to answering the question, of whether these cosmic wanderers really exist in the numbers we imagine, and if so, what secrets they carry. But perhaps the most important aspect of the dark comet mystery is not whether it will be solved, but what it teaches us about the nature of scientific inquiry and cosmic wonder. Science is often presented as a march toward complete knowledge, a systematic elimination of mystery and uncertainty. But the greatest scientists have always known that each answer generates new questions, that the island of knowledge is surrounded by an ocean of mystery that grows larger as the island expands. The dark comet hypothesis exemplifies this beautifully, showing us how a simple question, what happens to comets ejected from star systems, can open into a vast exploration of chemistry, biology, cosmology, and philosophy. The emotional and spiritual dimensions of contemplating dark comets shouldn't be overlooked. There's something deeply moving about the idea of these patient travellers carrying their cargo through the eons, connecting distant places and times through their simple existence. They embody a kind of a cosmic patience that our hurried age needs to remember, a reminder that important processes can unfold slowly, that not everything needs to happen quickly to be significant. They suggest a universe that is more connected than we imagined, where isolation is temporary and possibly illusory, where every part is connected to every other part through threads we're only beginning to see. As you drift towards sleep tonight, carried by these contemplations into your own journey through darkness, you might imagine yourself as a passenger on a dark comet, frozen in time but somehow aware, watching the galaxy slowly rotate around you, stars being born and dying like flowers blooming and fading in an eternal garden. You would see the universe not as a collection of separate objects, but as a continuous process, a flow of matter and energy constantly transforming, constantly creating new patterns and possibilities. Your journey would have no clear beginning or end, just an eternal now moving through an infinite space of potential. The mystery of dark comets thus becomes a mirror for the mystery of existence itself. Why is there something rather than nothing? How did complexity arise from simplicity? What is the purpose, if any, of this vast cosmic dance? Dark comets don't answer these questions, but they add depth to them, showing us that the universe might be stranger, more connected, more filled with hidden processes than we imagined. They remind us that mystery is not the enemy of knowledge, but its companion, not something to be eliminated, but something to be embraced, explored, and celebrated. In the end, the question, what if dark comets drift between the stars, is less important than the journey of exploration it initiates. Whether dark comets exist in the numbers we've imagined, whether they carry life between stellar systems, whether they play a crucial role in cosmic evolution, these specific questions matter less than the expansion of perspective they provide. They invite us to think on cosmic scales, to imagine processes that unfold over billions of years, to see ourselves as part of something vast and ancient and ongoing. They remind us that we live in a universe of wonders, most of which we haven't yet discovered, many of which we might never fully understand, but all of which contribute to the magnificent mystery of existence. Tonight, as you drift into sleep, you join the eternal dance of cosmic wanderers, your consciousness fading like a comet retreating into darkness, carrying within you the memories and molecules of countless stars, connected through invisible threads to every part of the universe. The dark comets, real or imagined, remind us that we are all travellers through space and time, all carrying precious cargo, all part of a story that began before we arrived and will continue after we're gone. In the darkness between the stars, in the patience of eternal journeys, in the slow transformation of matter into meaning, we find not answers but something better. An ever-deepening appreciation for the mystery and beauty of the cosmos we're privileged to contemplate. The universe keeps its secrets while inviting us to wonder, and in that invitation, in that eternal dance between known and unknown, between discovery and mystery, we find our purpose, our joy, and our peace. The dark comets drift on through the darkness, whether we observe them or not, carrying their ancient cargo toward unknown destinations, patient messengers in a cosmos that reveals itself slowly, partially, beautifully, ensuring that wonder never ends, that mystery never fully resolves, that the journey of discovery continues as long as consciousness exists to appreciate it. And in that continuation, in that eternal unfolding of understanding that never quite reaches completion, we find not frustration but fulfillment, not disappointment but delight, not an ending but an invitation to dream on through the darkness, carried like cosmic wanderers toward a dawn that never fully arrives but always promises new wonders just beyond the horizon of our understanding.